Have you ever gazed into the night sky and felt the weight of a question older than humanity itself? A question whispered across generations, carved into stone, etched in ink, spoken in awe. Where did all this come from? Why does the universe exist? And why, amid all this cosmic vastness, do we seem to be the only ones asking? Join us as we unravel one of the most enduring and profound mysteries known to humankind, the origin of everything. Our journey begins not with fire or fury, but with something infinitely dense and immeasurably small, a singularity. This is the Genesis, a time roughly 14 billion years ago when all matter, energy, space, and even time itself were compacted into an unfathomable state. What happened next is known today as the Big Bang, not an explosion in the traditional sense, but a monumental expansion. Space itself began to stretch, and from that stretch emerged the architecture of our reality. As the universe rapidly unfurled, temperatures plummeted, and in the cooling aftermath, particles formed. Quarks, electrons, and then atoms. Hydrogen and helium were born in abundance, the cosmic building blocks that would, over eons, gather under gravity's relentless pull. These clouds of primordial gas gave rise to stars, stars to galaxies, galaxies to clusters, and eventually the intricate cosmic web that binds the observable universe. Each gleaming star is a monument to that beginning, each galactic arm a ripple from the initial burst of creation. One of the most astonishing pieces of evidence for this grand origin story is the cosmic microwave background radiation, a ghostly glow that permeates all of space. Discovered by accident in 1965 by Arno Penzias and Robert Wilson at Bell Labs, this faint signal is the afterglow of creation itself, a leftover whisper from when the universe was merely 380,000 years old. At that time, the cosmos cooled enough for photons to travel freely, and those very photons now reach our detectors as microwave radiation. Modern space telescopes, such as the Planck satellite and the Wilkinson microwave anisotropy probe, have mapped this radiation with astonishing precision. Their measurements reveal minute fluctuations in temperature, tiny ripples that seeded the formation of galaxies. These subtle imprints tell a tale of a universe that began hot and dense, then stretched and cooled, slowly weaving the tapestry of cosmic structure. The redshift of distant galaxies offers yet another thread of this tale. First observed by Edwin Hubble in the 1920s, redshift shows that galaxies are moving away from us and from each other. The farther they are, the faster they recede. This discovery revealed a startling truth. The universe is still expanding. This observation aligns precisely with the predictions of the Big Bang model and gives us a kind of cosmic breadcrumb trail pointing back to that singular origin. Equally compelling is the abundance of light elements, hydrogen, helium, and traces of lithium, found throughout the universe. Their quantities match theoretical predictions of nucleosynthesis, the process that occurred minutes after the Big Bang, when the intense heat was just right to forge these elements in precise proportions. It's as though the early universe followed a recipe, one that has been meticulously verified by observation. Together, these pillars, the cosmic microwave background, galactic redshifts, and elemental abundances, form a robust framework supporting the Big Bang theory. They knit together a story that spans billions of years and billions of light years, connecting photons, atoms, galaxies, and us. But what came before the Big Bang? That question pushes us to the very edge of our knowledge. In the standard cosmological model, time and space themselves began with the Big Bang. Asking what came before is akin to asking what's north of the North Pole. It may be a question that defies the structure of the reality we know. Yet speculative theories in quantum mechanics and cosmology invite us to imagine what might lie beyond the veil. Some propose a quantum vacuum, a turbulent sea of probabilistic potential from which our universe was born via random fluctuation. Others imagine a cyclic cosmos, endlessly reborn in a loop of expansion and collapse. The idea of a multiverse suggests our universe may be one bubble in a vast foam of universes, each with its own laws and fate. These frameworks remain theoretical, but they ignite our imagination, suggesting that the Big Bang may not be the beginning, but merely the beginning of our story. The discovery of the cosmic microwave background itself was a testament to the unpredictable nature of scientific discovery. In the early 1960s, Penzias and Wilson were calibrating an antenna for satellite communication. They encountered a persistent hiss, noise that came from every direction. At first, they suspected pigeons nesting in the device. But when all local explanations were ruled out, it became clear. They had stumbled upon the oldest light in the universe, a discovery that would win them the Nobel Prize and change our understanding of the cosmos forever. Through curiosity, precision, and a bit of cosmic luck, we now hold clues to the birth of everything. And yet, the mystery remains, quietly humming in the background of space, waiting to be heard. But their efforts were plagued by a persistent and enigmatic sound. No matter where they aimed their antenna, toward the sky, away from urban centers, across the quietest corners of the Earth, the hum remained, unwavering and stubborn. Every possible terrestrial source of interference was investigated and eliminated. Urban radio signals, faulty equipment, atmospheric noise, all ruled out. Still, the noise endured. Desperate for answers, they reached out to experts, among them Robert H. Dicke at Princeton University. Dicke and his team had been deeply engaged in a different kind of quest. They were searching for residual heat from the universe's earliest moments, a relic of the primordial fireball predicted by the Big Bang Theory. When Arno Penzias and Robert Wilson described their puzzling discovery, a silent epiphany dawned. The noise they couldn't silence was, in fact, the faint echo Dicke's team had been trying to detect. This noise, uniform in every direction and devoid of earthly origin, was not interference, it was revelation. It was the cosmic microwave background radiation, a fossil of light from a time when the universe was just 380,000 years old, freshly cooled and finally transparent. Photons once trapped in a hot, dense plasma were suddenly free to travel. That freedom left a signature, a whisper across the fabric of space. Announced in 1965, the discovery became a cornerstone of observational cosmology. It was a serendipitous triumph, and it earned Penzias and Wilson the Nobel Prize in Physics in 1978. Their accidental breakthrough gave the Big Bang Theory its first robust observational support, validating decades of theoretical prediction. It also opened a cosmic window. Satellites like COBE, WMAP, and Planck would later refine this picture, mapping the CMB with astonishing precision and granting us a glimpse into the universe's infancy. Yet, for all its triumphs, the Big Bang Theory leaves us with profound questions. At the heart of the theory lies the singularity, a moment of infinite density and temperature where our current laws of physics collapse. The theory tells us that the universe expanded from this singularity, but it cannot describe what came before it, or even what before might mean in a universe where time itself began at the singularity. This conundrum has spurred the search for a deeper framework. Theories like string theory and loop quantum gravity aim to reconcile the vast with the minute, marrying general relativity with quantum mechanics to illuminate the origin story that remains shrouded in mystery. Another daunting challenge lies in the unseen: dark matter and dark energy. Together, they make up roughly 95% of the universe's mass energy content. The Big Bang Theory accounts for the visible universe, the stars, galaxies, and gas, but not for this vast, invisible majority. Dark matter exerts gravitational influence, holding galaxies together, while dark energy appears to push the cosmos apart at an accelerating rate. Despite their profound impact, both remain essentially unknown. Then there's the cosmic imbalance between matter and antimatter. According to the Big Bang, both should have been created in equal amounts. If that were so, they would have annihilated one another completely, leaving only radiation. But we exist. Galaxies exist. There is matter. Why? These open questions do not diminish the power of the Big Bang Theory. Instead, they push science forward, pointing to new physics beyond the current paradigm. Each mystery is an invitation to listen more closely to the cosmos, to tune our instruments more finely, and to explore the echo of creation still vibrating in the silence of space. But no matter existed yet, no stars, no planets, no life. And yet, the observable universe is composed predominantly of matter. This imbalance between matter and antimatter suggests a crucial, unresolved mystery. Why did matter win? According to the standard model of particle physics, matter and antimatter should have been produced in equal amounts during the universe's infancy. If that were the case, they should have annihilated one another entirely. And yet, here we are. Something tilted the scales, a process still not fully understood. This asymmetry remains one of the most profound questions in modern cosmology. These unanswered questions open up an even larger canvas, one that reminds us that the Big Bang Theory, while robust and supported by a wealth of observational data, is not the final word. It's a cornerstone in a story still unfolding, a single chapter in the vast cosmic narrative. Throughout history, scientists have proposed alternative theories about the universe's origin and evolution. One of the earliest challengers to the Big Bang was the steady-state theory. Formulated in the 1940s by Fred Hoyle, Thomas Gold, and Herman Bondi, it imagined a universe without a beginning or end. Instead of a singular, explosive event, this model proposed that new matter is continuously created to maintain a constant density as the universe expands. The appeal was philosophical as much as scientific, a universe that is eternal and unchanging on the grandest scales. However, this theory faltered as evidence accumulated, most notably the discovery of cosmic microwave background radiation and the redshift of distant galaxies, both of which supported the Big Bang model. Yet the urge to question and refine our models remains strong. Enter the cyclic universe, a theory that envisions the cosmos as endlessly expanding and contracting in a rhythm of creation and collapse. This idea traces its roots to ancient philosophical thought, but modern versions have been reinvigorated by developments in string theory. In one such model, our universe is one of many brains, multidimensional surfaces that periodically collide. These collisions trigger Big Bang-like events, igniting cycles of birth and rebirth. The cyclic model offers potential solutions to the puzzles the Big Bang leaves behind, like what preceded the singularity or how to reconcile quantum mechanics with general relativity. An extension of this idea is the ekpyrotic universe, a model named after the ancient Greek word for conflagration. Rather than beginning in a hot, dense state, this theory suggests the universe started cold and nearly empty. Energy and structure emerged not from an explosion, but from the slow, graceful collision of higher dimensional brains drifting through a larger cosmic landscape. Unlike the traditional Big Bang with its infinite temperatures and densities, the ekpyrotic model presents a universe born with a whisper instead of a roar. While elegant in theory, it remains speculative and awaits empirical support that can elevate it from hypothesis to consensus. Despite the allure of alternative models, the Big Bang Theory continues to dominate because of its predictive power and its alignment with multiple strands of observational evidence. One of its strongest pillars is our ability to measure the age of the universe, an endeavor that draws from different complementary techniques. Chief among them is the study of cosmic microwave background radiation, the faint afterglow of the early universe, first detected in 1965 by Arno Penzias and Robert Wilson. This ancient signal, further mapped in exquisite detail by satellites like WMAP and Planck, reveals temperature fluctuations that encode the physics of the infant universe. By interpreting these subtle imprints, scientists derive the geometry, composition, and age of the cosmos. That age, about 13.8 billion years, is corroborated by another method, the measurement of the Hubble constant, the rate at which the universe expands. Initially observed by Edwin Hubble in the 1920s through the redshifts of galaxies, the constant allows astronomers to calculate how long the universe has been expanding. By working backward from the observed distances and velocities of galaxies, one can approximate when it all began. Today's astronomers refine this calculation using advanced telescopes, space-based observatories like the Hubble Space Telescope, and comprehensive surveys of galactic movements. A third line of evidence lies closer to home, in the Milky Way's oldest star clusters. These globular clusters are dense swarms of ancient stars, some of which are nearly as old as the universe itself. By modeling their life cycles based on luminosity and temperature, scientists estimate their ages. These estimates act as lower limits on the age of the universe, further confirming the results derived from cosmic radiation and expansion metrics. The convergence of these methods tells us we are on the right track, but also that much remains unknown. The cosmos, it seems, guards its secrets well. And because the oldest stars still shining today must have formed after the universe began, their ages impose a crucial lower boundary on the universe's age. This simple yet profound idea, that the universe must be at least as old as its oldest contents, has become a cornerstone in cosmology. When scientists merge this constraint with data from the cosmic microwave background, precise measurements of the Hubble constant, and other independent lines of inquiry, they find themselves converging on a shared conclusion. The age of the universe, now widely accepted to be around 13.8 billion years, stands as one of the most robust achievements in modern science. The harmony between different observational methods doesn't just boost confidence in our measurements, it strengthens the entire framework by which we understand cosmic history. Yet, in our quest to trace the universe back to its beginning, we inevitably confront a concept both awe-inspiring and confounding: the singularity. In the vast tapestry of cosmology, singularities are not mere abstractions. They are mathematical inevitabilities that hint at realms where our physical theories falter. A singularity is defined as a region where density and gravitational forces become infinite, and space and time, as we know them, cease to function in familiar ways. Within the framework of general relativity, singularities emerge as natural endpoints, or beginnings. According to the Big Bang model, the universe originated from such a point, an infinitely compact and energetic state from which all matter and space unfurled. The equations of general relativity, crafted by Albert Einstein in the early 20th century, describe how mass and energy warp the fabric of space-time, shaping the motion of celestial bodies. When these equations are applied to the universe in reverse, rewinding the cosmic clock, they guide us to a time when all distances shrink to zero and temperatures soar without limit. This moment, the so-called initial singularity, is not directly observable. It's a theoretical construct, a place where the predictive power of our equations breaks down, not because of a flaw in logic, but because we are entering a regime where quantum effects become too significant to ignore. Black holes offer another context in which singularities manifest, this time on a much smaller, localized scale. In the hearts of these enigmatic objects, matter collapses beyond the event horizon to a singularity, a point of such extreme gravity that nothing, not even light, can escape its pull. The resemblance between the singularities of black holes and that of the early universe poses tantalizing questions. Are these singularities truly similar? Could studying one unlock the secrets of the other? These are the puzzles driving current theoretical research. To resolve the paradoxes and limitations posed by singularities, scientists are delving into new realms of physics. Theories such as string theory and loop quantum gravity attempt to reconcile general relativity with quantum mechanics, offering possible frameworks for a quantum theory of gravity. These pioneering efforts seek to smooth out the infinities of singularities, replacing them with more physically meaningful structures. Perhaps the Big Bang wasn't the absolute beginning, but a transition point, a bounce or a phase change in a grander cosmic cycle. Amid these complex theoretical landscapes, redshift remains a beautifully simple yet powerful observational tool, one that anchors us in empirical reality. It acts like a cosmic Doppler effect, stretching the light from receding galaxies into longer, redder wavelengths. This phenomenon was first systematically documented by Edwin Hubble in the 1920s, who noticed that distant galaxies exhibited redshifts that increased with their distance from Earth. This was the first direct evidence that the universe is expanding, a revolutionary discovery that shattered the long-held belief in a static cosmos. Hubble's observation became the foundation for what is now known as Hubble's law, a linear relationship between a galaxy's distance and its recessional velocity. By measuring the degree of redshift, astronomers could not only map the structure of the cosmos, but also estimate the rate at which it was stretching. This rate, known as the Hubble constant, has become a central focus in modern cosmology. Today, instruments like the Hubble Space Telescope and the James Webb Space Telescope provide unprecedented precision, allowing scientists to refine the value of the Hubble constant and, by extension, deepen our grasp of the universe's timeline. But redshift reveals more than motion. It tells a story, a tale of how galaxies drift apart, how structures evolve, and how the universe itself changes over time. It allows astronomers to peer back billions of years, capturing snapshots of the cosmos as it was, not as it is. Through redshift, the universe becomes a time machine, unfolding a narrative that began in mystery and continues to challenge the limits of human imagination. And it also allows scientists to peer into the depths of the universe's past. Because light from distant galaxies takes millions or even billions of years to arrive at Earth, each photon carries with it a snapshot of cosmic history frozen in time. We don't see galaxies as they are now, we see them as they were long ago. In this way, redshift acts as a time machine, mapping out a chronology of the evolving universe. From galaxy clusters to sprawling cosmic filaments, the shifting wavelengths of light help trace the grand architecture of the cosmos as it has slowly unfurled over billions of years. As astronomers peer deeper into space and higher redshift values, they approach epochs closer to the Big Bang itself. With each increment of redshift, we encounter a younger universe, one that was hotter, denser, and stranger. These ancient signals let us study the birth of the first stars, the chaotic formation of early galaxies, and the cosmic scaffolding built by dark matter. Moreover, redshift data serves as a crucial piece of a larger puzzle. When combined with observations of the cosmic microwave background, the faint afterglow of the Big Bang, and the arrangement of galaxy clusters, it helps refine our models of the universe's shape, its age, and its mysterious ingredients. Together, these lines of evidence have given rise to a remarkably cohesive picture. The universe has been expanding for approximately 13.8 billion years, and it is redshift, those spectral fingerprints left by ancient starlight, that has been among the most powerful tools guiding our understanding. But even as we unravel the story of cosmic expansion, one profound question continues to loom. What ignited it all? The origin of the Big Bang remains one of the most enigmatic puzzles in all of science. While we've mapped the aftermath in exquisite detail, the cause of the Big Bang itself lies shrouded in uncertainty. One prominent theory points to quantum fluctuations in an initial vacuum state. According to this idea, before time and space as we know them existed, a quantum vacuum may have teetered on the edge of instability. Governed by the rules of quantum mechanics, random fluctuations in this empty but energetic void could have triggered a violent and sudden release of energy, a birth cry that exploded outward to become our universe. Another revolutionary concept is cosmic inflation, first proposed by physicist Alan Guth in the early 1980s. Inflation theory suggests that an unimaginably rapid expansion occurred a fraction of a second after the Big Bang. Driven by a hypothetical field called the inflaton, this burst of exponential growth smoothed out any primordial irregularities and laid the groundwork for the more gradual expansion we observe today. Yet, inflation is not the end of the mystery. It is another beginning. For if inflation shaped our universe, what sparked inflation itself? Here, the notion of a multiverse emerges, an idea both radical and increasingly considered. Some theoretical models propose that our universe is just one of many, nestled within a grander cosmic landscape. Within this higher dimensional space, regions with different energy levels can undergo inflationary episodes independently. These pocket universes might arise endlessly, each governed by its own laws of physics. In such a framework, the birth of our universe was not unique. It was one ripple among countless others. A related and equally bold idea is the ekpyrotic model. It imagines that our universe was born not from a singular explosion, but from a collision. In this theory, our reality exists on a four-dimensional brane floating in a multidimensional space. Occasionally, these branes collide, releasing titanic amounts of energy and spawning a new universe in the process. This cyclical vision of creation replaces the singular Big Bang with a repeating cosmic heartbeat, each collision a new beginning, each retreat a quieting end. Finally, quantum cosmology seeks to go beyond even these sweeping concepts. By marrying general relativity with quantum theory, some researchers propose that the universe may not have had a beginning at all, at least not in the classical sense. One such idea is the Hartle-Hawking no-boundary proposal, which suggests the universe is finite but has no boundaries, like the surface of a sphere. In this view, time itself may have emerged from a quantum state, eliminating the need for a singular origin and reframing the Big Bang as a phase transition from a timeless quantum realm into the expanding universe we now inhabit. But unbounded, like the seamless surface of a sphere, our universe may have never needed a defined beginning, nor a singular explosive origin. This idea reshapes our understanding of time itself, suggesting that at the earliest moments of the cosmos, space and time were interwoven so intimately that their distinction becomes meaningless. Such a state defies our everyday perception of before and after, near and far. These radical propositions hint at what could have triggered the Big Bang, not as a singular event, but as a transition in a vast continuum. Yet, without observational confirmation or breakthrough theoretical models, these remain compelling speculations. Still, they challenge our intellectual horizons and reveal how profound and elusive the origin of the universe truly is. The theory of eternal inflation pushes this boundary even further. It is not merely an extension of cosmic inflation, it is a revolution. Originally introduced to address lingering questions in the Big Bang model, such as why the universe appears so flat or how regions so distant could look so similar, cosmic inflation proposed that the universe underwent an unimaginably rapid expansion within the first split second of its existence. But eternal inflation suggests something far grander, that this inflation may not have ended everywhere. Instead, it continues indefinitely in some regions, spawning an infinite array of isolated bubble universes within a boundless multiversal sea. At the heart of this concept lies the inflaton field, a theoretical energy field believed to have powered that original burst of inflation. As the field rolls toward its minimum energy state, it decays, allowing regions of space to settle and form structures like galaxies. But due to quantum fluctuations, not all parts of this inflaton field evolve uniformly. While some regions settle, others remain in an inflating state, giving rise to a cosmic patchwork. Some areas calm and structured like our own, others still wildly expanding. The result? A fractal cosmos, an infinite, ever-growing multiverse where each bubble may have its own set of physical laws, constants, and even dimensionality. This multiverse concept helps address some of the deepest mysteries in physics, such as why the constants of nature appear so perfectly tuned for life. If infinite variations of universes exist, then it's no surprise we find ourselves in one where life can emerge. It's simply one of countless possibilities. Yet this model presents a serious observational challenge. Because space between bubbles expands faster than light can travel, these universes remain forever disconnected. We can't see them, measure them, or communicate with them. And yet, their potential existence reframes everything. We may be one flickering island of order in an unfathomable cosmic archipelago. Enter chaotic inflation, a theory pioneered by physicist André Linde, which adds another dimension to this cosmic narrative. In contrast to earlier models that assumed a meticulously fine-tuned starting point, a uniform high-energy state, chaotic inflation allows for a beginning that is anything but tidy. It proposes that inflation can begin wherever the inflaton field happens to possess a high enough energy, without requiring a uniform field or a precise configuration. The universe, in this view, didn't emerge from a singular spark. It erupted spontaneously in pockets where conditions happened to be right. In this model, the inflaton field is allowed to take on a range of values across different regions of space. Its potential energy landscape might be as simple as a rolling hill, a quadratic or quartic potential, yet that simplicity leads to astonishing consequences. Because different regions of space hold different energy levels, some will naturally exceed the threshold for inflation, causing those patches to blow up exponentially. The randomness of these conditions makes inflation not just possible, but practically inevitable in at least some regions. What's more, chaotic inflation elegantly connects to eternal inflation. As one region completes its inflationary phase and cools into a bubble universe, others, scattered like seeds in a turbulent field, continue inflating, birthing new universes in an endless self-replicating cascade. It is a cosmos without a center, without an edge, and without a single timeline. It is a vision of creation not as a singular event, but as a perpetual unfolding, a universe that is eternally giving birth to itself. And as different regions of space-time undergo inflation, they drift apart, cut off from one another by the very fabric of expansion. This severing of causal ties doesn't just scatter matter, it births realms. Each isolated pocket becomes a universe unto itself, swelling with possibility. What emerges is not one universe, but a sprawling, perhaps infinite multiverse, a mosaic of countless bubble universes, each sealed within its own cosmic horizon. And within each bubble, nature may write its own rules. The laws of physics, the values of fundamental constants, even the dimensions of space could differ entirely. This randomness isn't a flaw, it's the feature. It offers a natural lens through which we can view the apparent fine-tuning of our universe without needing to assume precision at the beginning of everything. This vision is rooted in the idea of chaotic inflation, a model both radical and elegant. Unlike traditional inflationary theories that require specific initial conditions, chaotic inflation thrives on simplicity and uncertainty. It posits that inflation can begin in a patch of space with a wide range of conditions. As this region inflates, quantum fluctuations dictate its evolution, creating diversity from chaos. This randomness gives rise to countless bubbles, each a separate universe with its own identity. Chaotic inflation has drawn favor for its compatibility with high-energy physics, weaving itself seamlessly into frameworks like string theory and quantum cosmology. Its predictions aren't just theoretical dreams. They offer concrete fingerprints in the cosmic microwave background and the architecture of the large-scale universe. But the reach of inflation doesn't stop there. It branches out into eternal inflation, a staggering extension of the idea. Here, inflation never truly ends. While in some regions it halts, birthing new bubble universes, other regions continue to inflate endlessly. This recursive process suggests a cosmos that is not linear or cyclical, but fractal, a cosmic foam of constantly generating space-time. The inflaton field, the driver of this inflation, is not stable. It's jittered by quantum fluctuations, ensuring that some areas keep expanding while others fall out of inflation, crystallizing into distinct universes. These events are disconnected, like fireworks frozen mid-explosion across an unreachable sky. Each universe stands alone, forever unreachable from the next, each with its own past, future, and laws. String theory enters this panorama with its own metaphysical twist. It proposes that our three-dimensional universe may be a brain, a membrane floating in a higher dimensional space. In this brain world scenario, universes like ours are not solitary, but part of a higher dimensional sea. Interactions, collisions, or even ripples between these brains can spawn new universes, each a new sheet in an interdimensional atlas. These aren't mere abstractions. They emerge naturally from the mathematical landscapes of string theory, where solutions number not in dozens or hundreds, but in the billions. Each solution corresponds to a different vacuum state, a different universe with its own reality. Meanwhile, quantum mechanics lends its voice through the many worlds interpretation. First proposed by Hugh Everett in the 1950s, this radical idea asserts that every quantum decision, the spin of a particle, the path of a photon, splits the universe. Every possibility plays out in a separate, equally real universe. When you measure a particle, you're not collapsing a wave function, you're branching reality. If you flip a coin, the universe forks, heads in one, tails in another. These universes are inaccessible to one another, yet they coexist. Parallel timelines, endlessly diverging with each quantum twitch. These theories, cosmic inflation, string theory, quantum mechanics, don't compete, they converge. Together, they build a case for the multiverse, each offering a unique path to the same mind-bending conclusion. Our universe may be one of many. And into this theoretical framework steps the anthropic principle, a philosophical idea with scientific bite. It suggests that the reason we observe a universe fine-tuned for life is because we must. Only in such a universe could observers evolve to ask the question. In a multiverse teeming with variations, it's not surprising that one bubble, ours, just happens to be right. Eternal inflation casts the widest shadow, suggesting that this grand fractal cosmos will never cease generating new branches. Quantum fluctuations ensure that even as one region exits inflation and births a universe like ours, countless others remain locked in the inflationary state. They too will eventually spawn new bubbles. And so it continues endlessly, with space giving birth to more space in a self-replicating cascade. This fractal landscape isn't metaphorical, it's structural. Zoom in or out and the same pattern repeats. Universes within universes, layers within layers. A cosmic tree growing not in time, but in possibility. This fractal geometry stretches the imagination. It's not just a matter of how many universes exist, but how they're arranged. Geometry itself becomes complex, twisted by inflation into irregular webs. Some regions stretch and bend so wildly that familiar shapes break down. The space between bubbles becomes vast and inhospitable, a void where inflation reigns eternal. Yet each bubble, each node in this cosmic fractal, could harbor its own stars, galaxies, and perhaps life. In the end, the multiverse is not merely a speculation. It is the natural consequence of some of our best theories. If inflation is real, if quantum mechanics holds, if string theory offers a glimpse of deeper truths, then we are not alone. Not in the sense of extraterrestrial life, but in the deeper, more profound sense that our universe is but one brushstroke on an infinite canvas. The cosmic story may be bigger, stranger, and more beautiful than we ever imagined. But as a dynamically evolving hierarchical system, this vast cosmic structure reveals itself through relentless exponential growth, interrupted only by the emergence of countless bubble universes. These separate domains, each a universe in its own right, spread across an incomprehensibly vast tapestry, forming a recursive, self-similar pattern that transcends our ordinary notions of space and time. In this cosmic fractal, no two regions are exactly alike, yet all are born from the same underlying principle, eternal inflation. Through this radical lens, cosmologists seek answers to some of the deepest questions ever asked, about where we come from, what the universe truly is, and how endlessly varied its manifestations may be. Eternal inflation proposes that our universe is but a single bubble adrift in an infinite ocean of others. Each bubble represents an independent cosmos with its own physical laws, histories, and fates. The first clues pointing toward this idea emerged from the cosmic microwave background radiation, the faint afterglow of the Big Bang. Subtle quantum fluctuations in this background, first captured by the COBE satellite in the early 1990s and later refined by WMAP and Planck missions, offered evidence that the early universe experienced a period of extraordinary inflation. These minute irregularities provided the seeds for galaxy formation and hinted at something even more astonishing. Different regions of space might undergo inflation at varying rates, spawning isolated, self-contained universes, even as the inflationary process continues elsewhere. This is the heart of eternal inflation. It is not a process that ends, but one that constantly births new realities. Imagine space itself as a fertile expanse, where random quantum events, tiny fluctuations in energy fields, can give rise to entire universes. These inflationary pockets detach from the parent cosmos and grow independently, forever inaccessible to one another, yet eternally linked by their shared origin. The theory draws strength from the unifying pillars of modern physics, quantum mechanics, and general relativity. Quantum field theory allows for the vacuum to fluctuate spontaneously, unpredictably shifting energy densities. Such variations can trigger new rounds of inflation, birthing bubble after bubble in an ongoing cycle. Central to this process is the inflaton, a hypothetical scalar field theorized to drive inflation. According to physicists such as Nobel laureates Alan Guth and Andrei Linde, the inflaton's potential never settles completely. Instead, it fuels continuous inflation across different regions of spacetime, with isolated patches, our own universe among them, occasionally emerging from this ever-expanding sea. But the allure of eternal inflation lies not only in its philosophical implications, but also in its power to solve long-standing cosmological puzzles. Chief among them is the horizon problem. Why is the temperature of the universe so uniform in all directions, even in regions that should never have been in contact? The inflationary model provides a stunning answer. During the inflationary epoch, our universe expanded faster than the speed of light. This rapid growth stretched what was once a causally connected region, small enough for thermal equilibrium, to cosmic proportions. Thus, the uniformity we observe in the cosmic microwave background is not a mystery, but a natural consequence of inflation. In eternal inflation, this smoothing effect is replicated across every new universe. Each bubble inherits a moment of rapid inflation that irons out its irregularities and establishes conditions conducive to complex structures. Our universe is just one beneficiary of this mechanism. The horizon problem is therefore not a unique feature of our reality, but a universal trait of all bubble universes birthed through eternal inflation. Every time a new domain sprouts from inflating spacetime, it carries forward the initial coherence necessary to evolve into a structured cosmos. Taken together, the observational evidence, theoretical foundation, and explanatory power of eternal inflation suggests that we are part of a multiverse far more intricate and mesmerizing than any single universe model could offer. Far from being a closed story, our universe may be one chapter in a limitless cosmic epic, an ever-growing mosaic of realities, each with its own beginning, but no collective end. But an intrinsic resolution lies deep within the grand architecture of eternal inflation, a cosmic framework in which the laws of physics operate with remarkable consistency, orchestrating the emergence of uniform conditions across an unfathomable number of newborn realms. These realms, often referred to as bubble universes, owe their very existence to quantum fluctuations, the infinitesimal yet profoundly powerful tremors predicted by quantum mechanics. These fluctuations aren't just incidental, they are the vital sparks that ignite the birth of entire universes. Picture, if you will, the influent field, a theoretical scalar field thought to be responsible for the rapid inflation of the early universe. This field, like a vast, restless sea, is subject to tiny quantum jitters. At random points, these fluctuations momentarily elevate or diminish the energy density in localized patches of space. When a particular region experiences a surge in energy due to one of these fluctuations, it resists settling down. Inflation continues. Other regions, however, stabilize and transition into a more quiescent state. It is in these calmer zones that bubble universes crystallize, entire new cosmoses pinched off from the inflating backdrop. Imagine an infinite foam, ever expanding, where bubbles continuously form and drift, some growing large and mature, others still birthing from the high-energy froth. Each bubble is a universe, each with its own trajectory and potential. The inflating space between them ensures the process never ceases. In this cosmic sea, creation is not a one-time event, but a perpetual rhythm, driven by the random dance of quantum mechanics. These quantum fluctuations don't merely determine where inflation stops or continues. They leave behind subtle imprints, variations in density so minute that they seem trivial, yet over billions of years they become the seeds of structure. Galaxies, clusters, and the vast cosmic web all trace their origins to these initial differences. One fluctuation leads to a galaxy, another to an entire supercluster. The architecture of our own universe, with its staggering complexity and grandeur, begins in these quantum whispers. But the real marvel lies in how each bubble universe is shaped by its own unique pattern of fluctuations. This means no two bubbles are quite the same. Some may evolve under laws eerily similar to our own, while others could be governed by radically different physics, alien realities where time flows differently or where stars never form. The multiverse, then, is not a monotonous repetition, but a sprawling tapestry of divergent realities, each one spun from the same fundamental quantum loom. The inflaton field itself can be visualized as a vast landscape of peaks and valleys. As it rolls downward across this terrain, different regions settle into different valleys due to quantum nudges. Where the field's energy drops sharply, inflation halts, and a bubble universe begins to blossom. These pockets stabilize and expand at their own pace, becoming self-contained realms amidst an ocean of still inflating space. Around them, the field continues to churn, birthing more bubbles. This dynamic is evocatively captured by the metaphor of rising raisin bread. The dough represents the inflating space, the raisins, bubble universes. As the dough expands, more raisins appear. Each raisin grows, but remains distinct, isolated by the ever-expanding dough around it. Within this loaf of space-time, each bubble universe is a universe unto itself, with its own constants, its own laws, and perhaps its own form of life. Thus, eternal inflation offers a vision of a cosmos not merely vast in scale, but infinite in possibility. A cosmos where creation never ceases, where every quantum fluctuation holds the potential to birth a new reality, and where the very structure of existence is a living testament to the interplay between randomness and order, chaos and symmetry, chance and inevitability. Because they develop somewhat independently, shaped by the extraordinary conditions present at their inception, the birth of bubble universes within the framework of eternal inflation reveals a universe far more complex and dynamic than once imagined. This process is not a singular event, but an ongoing, never-ending cosmic phenomenon driven by the relentless dance between the forces of cosmic expansion and the peculiar quirks of quantum mechanics. Each new bubble universe emerges as a distinct realm, a unique pocket of reality with its own set of physical laws and properties, potentially vastly different from our own observable cosmos. The narrative that eternal inflation offers is nothing short of staggering. A multiverse perpetually swelling with countless realms of possibility, each bubble universe a world unto itself, unfolding independently amidst an ever-expanding cosmic sea. Yet, despite the grandeur of this concept, one of the most profound mysteries remains: the question of whether we could ever observe or interact with these other universes. From our current vantage point, steeped in the laws of physics as we understand them, the prospects of such interactions seem remote, if not outright impossible. When a bubble universe is born, it forms within an immense, exponentially expanding space, a backdrop so vast that the distances between these bubbles grow faster than any signal or particle can travel. This cosmic stretching effectively isolates each bubble universe behind its own horizon, a boundary beyond which no communication or observation can penetrate. The very fabric of space-time in this multiverse acts as an impenetrable barrier, locking these bubbles away from one another. Adding to this isolation are the domain walls, the boundaries between bubble universes, regions characterized by extreme and exotic physical conditions. These walls can harbor immense energy densities, creating powerful gravitational effects and hostile environments. Such barriers are not merely physical, but existential, making any form of travel or communication across universes beyond the reach of our current physics. Further complicating the picture is the possibility that each bubble universe's spacetime might differ so fundamentally in structure and composition that they are effectively incompatible. Differences in physical constants, dimensions, or forces could render these universes so alien that even theoretical interaction becomes an insurmountable challenge. Yet the story does not end in despair. While direct observation or communication with other bubble universes remains out of reach, indirect evidence may still offer tantalizing glimpses into their existence. If two bubble universes were to collide during their early development, the aftermath of such cosmic encounters could leave faint but detectable signatures, subtle anomalies imprinted on the cosmic microwave background radiation, the ancient afterglow of the Big Bang. Scientists tirelessly analyze precise data from satellites like Planck, searching for these faint fingerprints that could hint at the multiverse's shadow. Beyond observational efforts, groundbreaking advances in theoretical physics, in areas such as quantum gravity and string theory, may one day provide frameworks to understand these elusive interactions. Even if tangible communication or travel remains impossible, the exchange of information on highly abstract levels could reveal new dimensions of reality, enriching our understanding of existence itself. In this grand cosmic saga, eternal inflation reshapes our perception of the universe's scale and nature. Far beyond the vast cosmos described by the traditional Big Bang model, which itself speaks of a universe expanding from a singular event some 13.8 billion years ago, eternal inflation introduces the vision of an infinite, ever-growing multiverse. Our observable universe is but a tiny bubble, a speck within an endless cosmic ocean. During inflation, space expands exponentially, transforming tiny regions into immense expanses in the blink of a cosmic eye. This process, fueled by quantum fluctuations, continues endlessly, generating new bubble universes across the infinite expanse of inflating space. While each individual bubble, including our own, might be finite in size, the totality of the multiverse is potentially boundless, forever birthing new realities. This ongoing creation challenges our understanding of existence, inviting us to contemplate a cosmos far more intricate and mysterious than ever before. A multiverse brimming with diverse realms, where the possibilities for reality itself are infinite. But the space in which these universes form is relentlessly expanding, continuously spawning new bubble universes in an ongoing cosmic dance. This grand process is known as eternal inflation, and it suggests a multiverse far beyond anything we once imagined. The multiverse is not merely vast, it could be infinite with no bounds at all. This radical idea forces us to rethink everything about our cosmos. What we see as the entirety of the universe, the observable universe, might be just a tiny bubble among countless others, each with its own unique properties and laws. As these bubbles form and drift apart in this ever-expanding cosmic sea, the laws of physics that govern one bubble might be drastically different in another. Constants we consider fundamental, such as the speed of light, gravitational strength, or electromagnetic forces, could vary from one universe to the next. Imagine a reality where the familiar rules of nature no longer hold, where gravity behaves differently or light travels at altered speeds. The sheer scale of eternal inflation shatters the cosmological principle's assumption that the universe is uniform and the same in every direction. Instead, while individual bubbles might appear orderly, the entire multiverse could be a tapestry of incredible diversity and complexity. The implications stretch far beyond physics. They ripple into philosophy and metaphysics, challenging our concepts of existence, reality, and what it means to be universe. If the cosmos is indeed infinite and bursting with variety, how do we define our place within it? What does it mean to exist in just one bubble out of an endless cosmic froth? These questions open realms of contemplation as vast as the cosmos itself. Amidst these cosmic considerations lies the anthropic principle, a philosophical lens crafted to explain why our universe's physical constants seem perfectly tuned for life, especially intelligent life like us. At its heart, the anthropic principle argues that the universe's properties must be compatible with conscious observers. Otherwise, we wouldn't be here to notice them. There are two key versions of this principle: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The weak anthropic principle states that we observe the universe's life-friendly properties simply because only such a universe could harbor observers like us. For example, the precise strength of electromagnetic forces and the value of the cosmological constant are just right to allow stars to ignite, chemistry to unfold, life to evolve. When combined with the multiverse idea from eternal inflation, it suggests countless universes exist, many sterile and lifeless, but we happen to be in one where conditions align perfectly to nurture life. On the other hand, the strong anthropic principle goes even further, suggesting that the universe must inherently possess properties that enable life to emerge and evolve. Some interpretations of SAP propose a kind of cosmic necessity or purpose, where the universe is compelled to develop consciousness and life, weaving together cosmology and metaphysics in profound ways. This philosophical framework provides a compelling explanation for the remarkable fine-tuning we observe without resorting to a divine designer. It harmonizes well with the many worlds interpretation of quantum mechanics and the eternal inflation model, both depicting a cosmos filled with diverse universes where only a fortunate few support life. Critics, however, see the anthropic principle as tautological or unfalsifiable, a statement that can't be proven wrong. Yet, its role in the dialogue about cosmic fine-tuning remains a powerful and provocative piece of scientific thought. At the foundation of all this lie the physical constants, tiny numbers with colossal influence. These constants dictate the fundamental forces shaping everything from the smallest particles to sprawling galaxies. Even minuscule shifts in these values could yield a universe utterly hostile to life. Consider the gravitational constant, an extraordinarily small number, but without its precise value, stars would never form, planets wouldn't hold together, and life as we know it would be impossible. Thus, the eternal inflation model and the anthropic principle together paint a picture of a cosmos both boundless and finely tuned, a breathtaking blend of infinite possibility and delicate balance, forever inviting us to explore the deepest mysteries of existence. But it dictates the very strength of gravity, the invisible architect shaping the grand design of our cosmos. Gravity is the force that draws matter together, birthing stars and galaxies from clouds of gas and dust. If gravity were stronger, stars would blaze intensely but briefly, burning out before life could possibly arise. Conversely, if gravity were weaker, the universe might be a barren expanse, stars never igniting, galaxies failing to form, leaving a cold, dark void bereft of complexity or wonder. Another fundamental force governs the dance of atoms, the electromagnetic force, measured by the fine structure constant. This subtle yet powerful constant choreographs how atoms bond and molecules form, the chemical symphony underlying all matter. Even the slightest deviation could unravel this harmony. A marginal shift could disrupt the stability of essential elements like carbon, without which the complex molecules of life would never emerge. Imagine a universe where atoms falter, where the chemistry of existence dissolves before it can begin. Equally crucial is the strong nuclear force, the mighty glue holding protons and neutrons tightly bound within atomic nuclei. Should this force increase by a mere fraction, stars would fuse hydrogen into helium at such a furious rate that heavier elements necessary for life would become scarce. On the other hand, a weaker strong force would prevent nuclei from forming at all, stripping the universe of elemental diversity and extinguishing the possibility for complex chemistry and life itself. These forces and constants are not random. Their precise tuning is the foundation for everything we know. This remarkable fine-tuning sparks profound questions, inspiring the anthropic principle. The idea that the universe's laws are exactly what they are because only such a universe could give rise to observers like us. It suggests a cosmos finely balanced to nurture life, where the interplay of forces creates a stable stage for complexity to unfold, evolve, and flourish. Among the constants, the cosmological constant, linked to the mysterious dark energy accelerating the universe's expansion, plays a starring role. Had it been even slightly stronger or weaker, the universe's fate would have been drastically different. A universe expanding too fast would scatter matter before stars could coalesce, collapsing too fast would snuff out life's chances. Instead, the delicate value we observe enables a cosmos that expands gently, giving stars and planets billions of years to form, and life the time to arise. The strong nuclear force's exactness is equally breathtaking. A 2% increase would convert nearly all hydrogen to helium early on, robbing the cosmos of water and life's building blocks. A 2% decrease would dismantle atomic nuclei, leaving a barren universe devoid of stable atoms. Meanwhile, the weak nuclear force responsible for critical nuclear reactions in stars and processes like beta decay must remain finely balanced. Too strong or too weak, and star fusion cycles would falter, disrupting the creation and distribution of life-essential elements like carbon and oxygen. Together, these forces weave the tapestry of reality. Their extraordinary precision ensures atoms hold together, chemistry proceeds, stars shine, and life emerges. A subtle shift in any would spell a universe unrecognizable, inhospitable to complexity or consciousness. This cosmic fine-tuning continues to captivate scientists and philosophers, prompting us to ponder deeper mysteries. Are these constants unique? Could other universes exist with different laws? What does it mean for us, living in a universe so exquisitely calibrated to nurture life? The answers remain elusive, but the profound balance of these forces stands as a testament to the remarkable nature of our universe, where, against incredible odds, life can thrive. For instance, essential elements like carbon play a critical role in the formation of life, yet without a delicate balance in the universe's chemistry, carbon might never form stable compounds. This instability would severely limit the complex chemical reactions necessary for life to exist. Consider the mass ratio between electrons and protons. It is approximately 1 to weight-36. This seemingly simple ratio profoundly influences atomic and molecular chemistry. If this balance were significantly altered, the bonding properties of atoms would change drastically, possibly preventing the formation of vital molecules such as water and organic compounds, the very foundation of life as we know it. These examples of fine-tuning reveal an extraordinary precision within the cosmos, highlighting the intricate balance required to sustain life. The exact values of these constants and conditions appear almost as if purposefully set, allowing the complex chemistry and long-term stability that life depends upon. Some interpret this as evidence of intelligent design or a purposeful creator, while others invoke the anthropic principle, suggesting that only universes with such fine-tuned parameters could foster observers capable of reflecting on their own existence. Regardless of perspective, this fine-tuning remains one of the most profound and compelling features of our universe. Moving beyond the microscopic world, the type of star that a planet orbits dramatically influences that planet's habitability. Stars govern planetary conditions ranging from temperature and atmosphere to the potential for life-sustaining environments. Different stars emit distinct types and amounts of radiation, have varying lifespans, and influence planetary environments through stellar activity like flares and winds. These stellar factors collectively shape the so-called habitable zone, a critical region where liquid water, a cornerstone for life, can exist. Sun-like stars, classified as G-type main sequence stars, are often considered ideal for hosting habitable planets. Our own Sun, a G2V star, has a stable luminosity and a lifespan stretching around 10 billion years. This provides a lengthy and steady window during which life might arise, evolve, and flourish. The habitable zone around a Sun-like star is positioned at a distance that allows water to remain liquid on planetary surfaces, fostering relatively stable climates, neither too hot nor too cold, ideal for complex life development. In contrast, smaller M-type stars, known as red dwarfs, dominate the galaxy in numbers and boast lifespans that extend into trillions of years. This longevity presents an appealing opportunity for life to potentially evolve over immense stretches of time. However, red dwarfs bring significant challenges. Their habitable zones are much closer to the star because of their lower luminosity, often causing planets to become tidally locked, where one side permanently faces the star. This leads to extreme temperature differences between the day and night sides. Furthermore, red dwarfs are notorious for intense and frequent stellar flares, capable of stripping away planetary atmospheres or bombarding surfaces with harmful radiation, factors that severely threaten the emergence or survival of life. On the opposite end of the spectrum lie the massive and hotter A-type or O-type stars. These celestial giants have lifespans lasting only a few million to several hundred million years. Although their high energy output broadens the habitable zone, their rapid aging process and eventual violent death through supernova explosions leave little time for complex life to develop. The intense radiation emitted by these stars is also highly destructive to any nascent biospheres, making these stars less likely to nurture life. K-type stars, often called orange dwarfs, offer an intriguing middle ground. Cooler and dimmer than G-type stars, they present a balanced environment that might combine some of the longevity advantages of red dwarfs with a more stable and less hostile radiation environment. Their habitable zones sit comfortably, potentially allowing planets to maintain temperate climates supportive of life. Together, these celestial factors, from atomic scale constants to the types and behaviors of stars, compose an intricate cosmic symphony. This finely tuned orchestra makes possible the rare conditions under which life can emerge, evolve, and perhaps thrive. The universe, in its vastness and precision, challenges us to ponder how extraordinary the environment must be to cradle life's fragile spark. But more stable than red dwarfs, K-type stars boast remarkably long lifespans, ranging from 15 to 30 billion years. Their habitable zones, while closer to the star than those of Sun-like stars, sit at just the right distance to avoid the pitfalls of tidal locking. This delicate balance means planets orbiting K-type stars might enjoy more stable climates and longer evolutionary windows for life to emerge and flourish. The nature of a star shapes the destiny of its planets. Sun-like stars create familiar environments conducive to life's rise, yet other stellar types present their own sets of opportunities and hurdles. From the enduring habitable zones of red dwarfs to the energetic realms of orange dwarfs and the brief, intense lives of massive stars, each star type weaves a unique thread into the complex fabric of potential habitats scattered across our galaxy. Water emerges as the cornerstone of planetary habitability, a vital ingredient that transcends its simple appearance. It serves as the essential medium for countless biochemical reactions, regulates climate, and shapes environmental conditions critical to sustaining life. The extraordinary properties of water make it indispensable. It acts as a universal solvent, enabling the intricate dance of proteins, nucleic acids, and cellular machinery within living organisms. This aqueous environment facilitates the transfer and transformation of energy and nutrients, driving processes fundamental to life: metabolism, DNA replication, and cellular respiration. The polarity of water molecules allows it to dissolve a vast array of substances, transporting nutrients and removing wastes inside organisms. On a planetary scale, water plays a crucial role in climate moderation. Its high specific heat capacity means it can absorb and store immense amounts of heat with only slight changes in temperature, buffering the planet against extreme fluctuations that could otherwise be lethal to life. Earth's vast oceans stand as a testament to this. They soak up the sun's heat during the day and release it slowly at night, creating a stable, hospitable environment over geological timescales. Moreover, the presence of liquid water on a planet's surface often signals a stable, protective atmosphere, one that shields life from harsh stellar radiation and maintains pressure conditions allowing water to remain liquid. This habitable zone, often called the Goldilocks zone, is the region where temperatures are just right, neither too hot nor too cold for liquid water to persist, making planets within it prime candidates for life. Water also drives dynamic planetary processes essential for maintaining habitability. On Earth, the water cycle, evaporation, condensation, and precipitation, regulates weather patterns and redistributes heat globally. Water's role in erosion and sedimentation helps form soils and rocks, creating diverse habitats and recycling nutrients vital for ecosystems. Furthermore, water interacts with carbon dioxide in the carbonate-silicate cycle, a planetary thermostat that regulates atmospheric CO2 and sustains a stable greenhouse effect to keep the planet warm enough for life. The role of water in habitability extends far beyond its chemical properties. It moderates climate, stabilizes temperatures, and participates actively in geological and atmospheric processes that nurture life-friendly environments. Its unique characteristics make water a key focus in the search for potentially habitable exoplanets, as the presence of liquid water drastically increases the odds of life beyond Earth. The distance from a planet to its star remains one of the most critical determinants of habitability because it sets the surface temperature and the possibility of liquid water. This optimal zone, the habitable or Goldilocks zone, encompasses a sweet spot where conditions allow water to remain liquid on a planet's surface. Too close to the star, near the inner edge of this zone, and a planet may suffer scorching heat, triggering a runaway greenhouse effect akin to Venus. Intense stellar radiation could vaporize surface water and trap heat with water vapor, a potent greenhouse gas, leading to soaring temperatures that render the planet inhospitable. Over time, this heat can even strip away the atmosphere, further diminishing the planet's life-supporting potential. On the other hand, planets beyond the outer edge of the habitable zone endure frigid conditions where water freezes into thick ice. Such environments, reminiscent of Mars or icy moons like Europa and Titan in our solar system, may hide subsurface liquid water beneath their frozen surfaces. These hidden reservoirs raise intriguing possibilities for life thriving in isolated niches beneath layers of ice, sustained by internal heat sources or chemical energy. In the grand cosmic ballet, the interplay between stars, water, and planetary distance crafts a vast spectrum of possible worlds. Each star type offers a different stage, while water remains the unifying force that could transform barren rocks into vibrant ecosystems. Understanding these relationships deepens our search for life beyond Earth and fuels the hope that somewhere in the galaxy, the conditions align perfectly for life to not only emerge, but to thrive. But the surface conditions would be far too cold to support liquid water, making life as we know it impossible in those regions. The habitable zone, often called the Goldilocks zone, is not a fixed boundary. It shifts and changes depending on the star's type and brightness. For example, Sun-like stars classified as G-type main sequence stars have a habitable zone stretching roughly from 0.95 to 1.4 astronomical units AU away, 1 AU being the average distance from Earth to the Sun. For smaller, cooler stars, the M-type red dwarfs, the habitable zone lies much closer, sometimes only a fraction of an AU from the star. This proximity brings its own unique challenges. Planets there face intense stellar flares, powerful bursts of radiation that can strip away atmospheres and batter surfaces. Additionally, many of these planets become tidally locked, meaning one side eternally bakes in starlight while the other remains in perpetual darkness, creating extreme temperature swings that challenge the persistence of life. And it's not just the type of star that shapes habitability. A planet's own characteristics dramatically influence whether it can sustain life. A thick atmosphere rich in greenhouse gases like carbon dioxide can trap heat, allowing liquid water to exist farther from the star than it otherwise might. Earth itself is a shining example, with its balanced atmosphere and vast oceans distributing heat evenly across the globe, maintaining a stable environment hospitable to life. In contrast, a planet covered in reflective ice or dense clouds might deflect so much stellar energy that it can survive even closer to its star, avoiding overheating. The shape of a planet's orbit also matters. Planets with nearly circular orbits enjoy stable climates, while those with highly elliptical orbits endure wide temperature fluctuations as their distance from the star changes drastically over time. Distance from the host star fundamentally dictates a planet's surface temperature and its potential to harbor liquid water, a critical ingredient for life as we understand it. The habitable zone sets the stage, but other factors such as atmosphere composition, star type, and orbital dynamics decide the actual habitability. This complex interplay reveals that life-supporting worlds may be rarer or more diverse than a simple zone around a star might suggest. The term Goldilocks zone draws from the familiar fairy tale where Goldilocks finds the porridge neither too hot nor too cold, but just right. Similarly, this zone marks the sweet spot around a star where a planet can hold onto liquid water without it freezing or evaporating. Around stars like our Sun, the zone stretches roughly between 0.95 and 1.4 AU, providing just the right amount of warmth. For cooler stars like red dwarfs, this zone is squeezed much closer to the star, from about 0.1 to 0.3 AU, demanding planets orbit near to get sufficient warmth. Yet this closeness comes with the cost of more frequent and intense stellar flares, making survival a challenge. On the other hand, hotter, more luminous stars push the habitable zone farther out, sometimes several astronomical units away, due to their higher energy output. But habitability isn't solely about being in the right spot. The planet's atmosphere is a decisive factor. A dense atmosphere with greenhouse gases can extend the habitable zone by holding in heat, whereas a thin or absent atmosphere might doom a planet to freeze, despite being within the classic bounds. Furthermore, the traditional concept of the habitable zone doesn't capture subsurface environments that may sustain life. Within our own solar system, moons like Europa and Enceladus orbit far beyond the Sun's habitable zone, yet harbor oceans beneath their icy crusts. These hidden environments challenge the notion that life requires the surface conditions defined by the Goldilocks zone, expanding our understanding of where life might exist beyond the classic model. In essence, the Goldilocks zone is a vital starting point for the search for life, but the universe's complexity ensures that habitability is a nuanced and multifaceted puzzle. Understanding these factors deepens our quest to find not just Earth-like worlds, but diverse habitats where life might thrive under extraordinary conditions. But beneath the frozen surfaces of some distant worlds lie hidden oceans, vast and mysterious, warmed not by sunlight but by the planet's own internal fires. These subsurface seas, tucked beneath thick icy shells, owe their existence to geothermal energy, heat generated deep within, stirring liquid water that may harbor the essential ingredients for life. Yet, life's potential is shaped not only by these hidden oceans, but also by the intricate dance of planetary orbits. Planets with elongated elliptical paths around their stars endure extreme swings in temperature, creating harsh and fluctuating environments that challenge the emergence of stable, life-supporting climates. In contrast, worlds tracing near-perfect circles in their stellar orbits enjoy more predictable conditions, increasing the chances for life to take hold and flourish. Central to the quest for extraterrestrial life is the concept known as the Goldilocks zone, a celestial sweet spot encircling a star where temperatures allow liquid water to exist on a planet's surface. This region, neither too hot nor too cold, represents a fundamental target for astronomers hunting for worlds that could support life. However, the boundaries of this zone are far from fixed. They shift and bend depending on a star's brightness, the planet's atmosphere, and its orbital dynamics, painting a complex portrait of habitability. Factors such as thick greenhouse atmospheres can extend the zone outward, while thin atmospheres pull it closer in, making each exoplanet's habitability a unique puzzle piece in the cosmic tapestry. Yet, even within this habitable range, there is another crucial shield silently at work: the planetary magnetic field. Generated by the roiling molten metals deep inside a planet's core, this invisible force field serves as a guardian against the relentless bombardment of stellar radiation. By deflecting charged particles, electrons and protons hurled through space by stellar winds, these magnetic shields protect a planet's atmosphere from being slowly stripped away into the void. Without this protection, the delicate balance needed for life could unravel, as harsh solar radiation erodes the very air that sustains organisms. Mars stands as a cautionary tale in this regard. Once cloaked in a thicker, denser atmosphere and flowing water, Mars lost its magnetic field eons ago. Left defenseless, the relentless solar wind gradually stripped away its air, transforming a once potentially habitable world into the cold, barren desert we see today. This dramatic atmospheric loss illustrates the magnetic field's essential role in preserving conditions suitable for life. Moreover, these magnetic fields do more than preserve atmospheres. They shield planetary surfaces from the high-energy ultraviolet and cosmic rays that can wreak havoc on biological molecules, including DNA. By diverting many of these charged particles toward the poles, magnetic fields give rise to breathtaking auroras, nature's shimmering light shows. Yet, beyond their beauty, these displays mark a crucial survival mechanism, reducing surface radiation and making a planet's environment far more hospitable for living organisms. Earth's magnetic field further supports life by maintaining climate stability. It acts indirectly to protect the ozone layer, a vital atmospheric shield that absorbs the sun's most harmful ultraviolet radiation. When the ozone layer remains intact, the climate system stays balanced, and biological processes continue without interruption. The interplay between magnetic fields and atmospheric integrity thus underpins the delicate environmental equilibrium needed for diverse ecosystems to thrive. Interestingly, the presence of a magnetic field also hints at a geologically active planet. The dynamo effect, which generates these fields, depends on the movement of a molten, convective outer core, a sign of internal heat and geological processes. This activity fosters plate tectonics and volcanic eruptions, mechanisms essential for recycling nutrients and regulating the planet's long-term climate through processes like the carbon silicate cycle. Such geological vitality is another thread in the complex fabric of planetary habitability. Yet, magnetic fields are not an absolute requirement for life. Some intriguing moons in our own solar system, such as Europa orbiting Jupiter and Enceladus circling Saturn, lack strong magnetic shields yet harbor subsurface oceans beneath their icy crusts. These hidden seas might offer refuge to life, protected by the ice and warmed by tidal forces exerted by their massive host planets, suggesting that life could persist in even more varied environments than once imagined. The quest to understand planetary habitability is a story woven from many threads: hidden oceans, orbital paths, habitable zones, protective magnetic shields, and internal geological engines. Each factor, working in concert, shapes the delicate conditions that might allow life to spark and endure across the vast reaches of the cosmos, but are still considered promising candidates for life because of their hidden subsurface oceans, warmed not by sunlight, but by the relentless internal geological activity beneath thick, protective ice shells. These vast, concealed oceans lie shielded from the harshness of space radiation by miles of ice, creating sanctuaries that defy the absence of a global magnetic field. This challenges the long-held belief that a magnetic field is the definitive criterion for habitability. Instead, it reveals that while a magnetic field offers undeniable benefits, it is not the sole guardian of life's potential. Planetary magnetic fields play a pivotal role in preserving habitability. They protect fragile atmospheres from solar wind erosion, reduce the bombardment of harmful surface radiation, and foster climate stability over geological timescales. Acting as a shield against space weather and intense cosmic radiation, these fields create safer environments where life can take root, evolve, and flourish. Yet, the presence of a magnetic field, although highly advantageous, is not an absolute prerequisite for all life forms. It simply elevates the likelihood that a planet can sustain life as we understand it. This insight fuels the ever-expanding quest to discover life beyond Earth, guiding scientists to consider worlds both with and without such magnetic shields. While Earth's life is undeniably carbon-based, Dependent on water as a solvent and oxygen to sustain metabolic processes, astrobiologists boldly venture beyond these familiar boundaries. They speculate on alternative biochemical frameworks that could thrive in radically different environments, biochemistries that defy the terrestrial template and broaden the horizons of where life might exist. Among the most fascinating possibilities is silicon-based life, a concept that draws from silicon's position right beneath carbon on the periodic table. Like carbon, silicon can form 4 chemical bonds, opening the door to complex molecular structures. However, the stability of silicon-oxygen bonds, especially at elevated temperatures, suggests that silicon-based life might be more feasible on worlds far hotter than Earth. Yet, a significant challenge remains. Silicon dioxide, or silica, is solid across a broad temperature range, potentially restricting the fluidity and versatility essential for life's chemistry. Still, in environments with thick, silica-rich atmospheres, the emergence of silicon life forms might be plausible, inviting us to imagine ecosystems beyond our wildest Earth-centric dreams. Ammonia-based life presents another compelling alternative. Ammonia shares many properties with water. It can dissolve organic molecules and supports a wide range of chemical reactions. Its notably lower freezing point, around -78 degrees Celsius, allows it to remain liquid in far colder environments than those hospitable to water-based life. Though hydrogen bonds in ammonia are weaker than those in water, they might still provide sufficient molecular stability for biological processes. This possibility suggests that planets or moons rich in ammonia could harbor life forms adapted to icy alien worlds where water is permanently frozen. Then there is Titan, Saturn's enigmatic largest moon, with its lakes of liquid methane and ethane. Here, the tantalizing prospect arises of methane or ethane-based life. In the frigid temperatures around -180 degrees Celsius, these hydrocarbons exist as liquids and could serve as solvents for biological systems utterly alien to terrestrial life. Such cryogenic life forms would depend on metabolic pathways fundamentally different from ours, given the lower energy yields typical of hydrocarbon chemical reactions. This invites a redefinition of life's biochemistry, encompassing forms that thrive where warmth and water are absent. Finally, in the sulfur-rich environments of Earth's deep-sea hydrothermal vents, sulfur-based life thrives, illustrating that even on our home planet, life has adapted to extremes. Sulfur compounds here play a central role in the metabolism of extremophiles, organisms that subsist in conditions once thought inhospitable. These sulfur-centric biochemical processes expand our understanding of how life can harness diverse chemical elements to sustain itself. Together, these diverse biochemistries, from silicon to ammonia, methane to sulfur, demonstrate that life's possibilities stretch far beyond the familiar patterns found on Earth. They compel us to look deeper and wider in our search for life in the cosmos, reminding us that the universe may host living worlds of astonishing variety, each adapted to its own unique environment. The absence of a magnetic field, the presence of exotic solvents or unusual chemistries, all are pieces of the grand puzzle that is habitability, inviting humanity to keep searching, keep exploring, and keep wondering what forms life might take beyond our pale blue dot. Some microorganisms defy the traditional reliance on sunlight by harnessing hydrogen sulfide, or H2S, in a remarkable process called chemosynthesis. In this process, chemical reactions involving sulfur compounds generate energy without the need for light, revealing the incredible adaptability of life. Imagine entire ecosystems thriving in the crushing darkness of deep-sea vents, fueled by this sulfur-based biochemistry. Such life forms offer a tantalizing clue to what might exist beyond our planet. And if we expand our gaze to other worlds, the possibility emerges that similar sulfur-based life could flourish on distant planets or moons, where sulfur compounds are abundant. For example, the frigid moon Titan, with its lakes of liquid hydrocarbons such as methane and ethane, poses a completely different chemical landscape. Unlike water, these hydrocarbons are poor solvents for ionic substances, meaning that any life forms that arise there would have to rely on non-polar biochemistry. This presents unique challenges in acquiring nutrients, processing waste, and storing energy, demanding adaptations far removed from those we know on Earth. But the intrigue doesn't end there. Scientists speculate that life elsewhere could employ biochemical pathways radically different from terrestrial norms. Take arsenic, for instance, an element toxic to most earthly organisms, but proposed as a potential substitute for phosphorus, a cornerstone of DNA and ATP, the energy currency of life. Although this idea is still debated, it opens the door to imagining life built on exotic chemistries, capable of surviving in extreme environments marked by intense radiation, extreme acidity or alkalinity, or crushing pressures. Such extreme environments may nurture organisms powered by novel energy sources, radiation, electrical conductivity, or entirely foreign metabolic cycles that recycle unusual elements in ways we can barely conceptualize. While these ideas remain speculative, they profoundly broaden our understanding of life's potential diversity across the cosmos. By embracing these possibilities, astrobiologists expand their search parameters, exploring worlds once dismissed as inhospitable. This inclusivity reshapes our approach to detecting extraterrestrial life, whether in the depths of our solar system or across distant exoplanets many light years away. At the heart of this quest lies the enigmatic Drake equation, devised by astronomer Frank Drake in the early 1960s. This formula challenges us to quantify the factors influencing the existence of intelligent civilizations, from the rate of star formation in our galaxy, to the fraction of stars with planetary systems, to the number of planets capable of supporting life. While many of the equation's terms involve educated guesses, current data suggests the Milky Way alone may harbor billions of Earth-like planets within habitable zones where liquid water can exist. The Kepler Space Telescope, launched in 2009, has dramatically advanced this knowledge, confirming nearly 3,000 exoplanets, some exhibiting conditions strikingly similar to our own. Yet, the discovery of microbial life remains a profound milestone, while the emergence of intelligent, communicative civilizations presents an even more elusive frontier. The probability hinges on a cascade of factors: how often life arises, how frequently it evolves intelligence, and how long civilizations endure. Optimists, inspired by the universe's staggering scale, estimated to contain around 100 billion galaxies, argue these odds favor the existence of other intelligent beings. Skeptics, wary of the many unknowns embedded in the Drake equation, urge caution and humility. Still, every new discovery stokes our anticipation, leaving us suspended between hope and mystery, wondering whether contact with extraterrestrial intelligence is imminent or if we are destined to be solitary voyagers in this vast cosmic ocean. Parallel to this cosmic inquiry, quantum mechanics probes the very fabric of reality at the tiniest scales. This branch of physics unravels the behavior of particles such as atoms and subatomic components, offering insights that challenge classical intuitions. The strange, probabilistic nature of quantum phenomena underpins much of the universe's complexity and might one day illuminate deeper truths about the origins and workings of life itself. Fascinatingly, the field of quantum mechanics took shape in the early 20th century when scientists confronted mysteries that classical physics simply couldn't unravel. At its core, quantum mechanics unveils a universe utterly alien to our daily perceptions, a realm where particles defy conventional rules and exist in multiple states simultaneously, a phenomenon known as superposition. Imagine an electron not fixed in one location around an atom's nucleus, but rather spread across a hazy cloud of probabilities, awaiting measurement to reveal its position. This challenges everything we thought we knew about matter and motion. Moreover, quantum mechanics introduces one of its most bewildering phenomena: entanglement. Here, particles become so deeply intertwined that the state of one instantly influences the state of another, no matter the vast distance between them. Albert Einstein famously described this eerie connection as spooky action at a distance, highlighting its baffling defiance of classical ideas about space and causality. These enigmatic behaviors are elegantly captured in the mathematical frameworks of Schrödinger's wave equation and Heisenberg's uncertainty principle, which together form the backbone of quantum theory. Schrödinger's equation tracks how the quantum state of a system evolves over time, while the uncertainty principle reveals a fundamental limit. It is impossible to precisely determine both the position and momentum of a particle at the same time. Despite these principles seeming counterintuitive, quantum mechanics is far from abstract theory. It forms the foundation for many modern technologies that permeate our lives, from the semiconductors powering our computers and smartphones, to lasers used in everything from surgery to telecommunications, and the MRI machines revolutionizing medical diagnostics. The quantum world, though invisible, shapes the tangible realities of our everyday existence. Delving deeper into this strange landscape, virtual particles emerge as one of quantum mechanics' most extraordinary features. They offer a glimpse into the restless, fluctuating fabric of what we commonly consider empty space. Even in a perfect vacuum, energy fluctuations give rise to pairs of particles and antiparticles that fleetingly appear and vanish. These are the virtual particles. Unlike real particles bound by strict conservation laws of energy and momentum, virtual particles exist transiently, allowed by the Heisenberg uncertainty principle, which permits momentary violations of energy conservation within unimaginably brief intervals. Physicists visualize these ephemeral interactions through Feynman diagrams, schematic illustrations in quantum field theory that depict how virtual particle pairs emerge, interact, and annihilate, returning energy back to the vacuum from which they sprang. This continuous invisible dance has profound consequences. One remarkable manifestation is the Casimir effect, where two uncharged metallic plates placed extremely close in a vacuum experience an attractive force. This force arises from the pressure difference created by virtual particles between and outside the plates, providing undeniable evidence that even empty space is teeming with activity. These discoveries revolutionize our understanding of the cosmos, revealing that a vacuum is anything but void. It is a dynamic arena brimming with quantum fluctuations, challenging our most basic assumptions and opening doors to new technologies and deeper mysteries about the fabric of reality itself. At the most fundamental level, the universe is alive with activity, an endless dance of particles and energy that exists in the realms we cannot directly observe, yet profoundly shapes the nature of reality. One of the most captivating phenomena at this scale is quantum foam, also known as space-time foam. Imagine the fabric of the universe not as a smooth, stable backdrop to events, but as something more turbulent, filled with incessant fluctuations that create a chaotic, frothy structure at the quantum level. This concept, introduced by the legendary theoretical physicist John Wheeler in the 1950s, arose from a deep need to reconcile general relativity, which describes the gravitational forces on the largest scales of the universe, with the principles of quantum mechanics, which governs the smallest particles. The essence of quantum foam suggests that at incredibly tiny scales, unimaginably smaller than anything we can see or measure directly, space-time is not a serene and continuous expanse, but a turbulent, frothy sea. At what scientists call the Planck scale, roughly 100 million trillion trillionths of a centimeter. That's a 1 followed by 35 zeros in the denominator, or 10 to the minus 35 meters. The fluctuations in energy are so intense that they distort space-time itself, creating transient wormholes, bubbles, and distortions that pop in and out of existence. This activity is so minuscule, yet so crucial, that it challenges our understanding of reality, offering a window into a deeper, more mysterious fabric of the universe. The Heisenberg uncertainty principle is a cornerstone of quantum mechanics and underpins the very idea of quantum foam. It suggests that certain pairs of properties, such as a particle's position and momentum, cannot be simultaneously known with absolute precision. This uncertainty is not just a limitation of our measuring instruments, but a fundamental feature of nature itself. It reveals that particles at the quantum scale are not locked in fixed states, but are subject to inherent fluctuations. These fluctuations are not just abstract mathematical constructs. They have real physical consequences. One of the most fascinating outcomes of this uncertainty is the phenomenon of virtual particles. According to the Heisenberg uncertainty principle, the product of uncertainty in energy and time has a lower bound. This means that over extremely brief intervals, energy can fluctuate in such a way that particles can spontaneously appear and disappear. These virtual particle-antiparticle pairs pop into existence in what appears to be an empty vacuum, only to vanish almost immediately. This process is so fleeting that it does not violate the conservation of energy. In essence, the uncertainty in energy allows the vacuum of space itself to teem with activity, even when there seems to be nothing there at all. This restless dance of virtual particles is a manifestation of vacuum energy, a concept that challenges the classical notion of a vacuum as a simple emptiness. Instead, quantum mechanics reveals the vacuum as a seething cauldron of energy, constantly fluctuating, never at rest. These energy fluctuations provide the wiggle room that allows virtual particles to emerge and disappear in such short time spans that they leave no lasting imprint on the larger universe. This dynamic, invisible activity is critical for our understanding of the quantum vacuum and the underlying workings of the cosmos. Moreover, the influence of vacuum energy extends beyond theoretical ideas. It plays a pivotal role in phenomena such as Hawking radiation, which occurs near the event horizon of a black hole. Here, vacuum energy can create a particle-antiparticle pair, with one particle falling into the black hole and the other escaping. The escaping particle carries away energy, leading to a gradual loss of mass from the black hole. This process, though a product of the quantum fluctuations of space, has profound implications for the nature of black holes and the fate of information within them. Another striking demonstration of the power of vacuum energy is the Casimir effect. When two uncharged metal plates are placed very close together in a vacuum, the energy fluctuations in the quantum vacuum between them create an attractive force that pushes the plates together. This effect, though minuscule on everyday scales, provides a concrete, observable result of the quantum vacuum's existence and its tangible effects on the physical world. These quantum phenomena reveal a universe dynamic and complex than our everyday experience suggests. Quantum foam, virtual particles, vacuum energy, and the uncertainty principle are not just abstract ideas, but fundamental aspects of the reality we live in. They challenge our traditional views of space, time, and matter, urging us to rethink the very nature of existence. Through these concepts, we catch glimpses of a deeper, more intricate universe, one that operates on scales far beyond our perception, yet shapes the very fabric of the cosmos. In our pursuit to understand the quantum gravity that unites the principles of relativity and quantum mechanics, these phenomena offer tantalizing clues. As we push the boundaries of scientific inquiry, the mysteries of quantum foam and vacuum energy will continue to inspire exploration and challenge the way we view the universe. They remind us that even in the emptiest spaces, there is an immense, invisible activity shaping the cosmos in ways we are only beginning to comprehend, but has measurable physical consequences. Thus, vacuum energy emerges not as mere emptiness, but as a profound force driving the very fabric of reality. It underpins the spontaneous creation of particles, influencing phenomena that span from the microscopic realm to the vastness of the cosmos. The vacuum, far from inert, is a dynamic and vital component of the quantum universe, constantly fluctuating with energy that breathes life into matter itself. Quantum fluctuations are at the heart of matter's genesis, ripples in the intricate fabric of space-time that blossomed into the galaxies, stars, and planets we witness today. These fluctuations, tiny, random changes in energy within a vacuum, arise inevitably from the Heisenberg uncertainty principle, a fundamental rule that forbids absolute certainty in measuring energy and time simultaneously. In the universe's infancy, mere fractions of a second after the Big Bang, a period known as inflation rapidly expanded space, stretching these minute fluctuations from the quantum scale to cosmic dimensions. As this inflation stretched the cosmos, quantum fluctuations became the seeds from which all matter grew. Regions with subtly higher or lower energy densities acted as gravitational wells, drawing in matter and sculpting the colossal cosmic structures we observe now. Remarkably, this theoretical narrative finds robust support in empirical data. The cosmic microwave background, CMB, the faint afterglow of the Big Bang, serves as a snapshot of the universe when it was just 380,000 years old. The delicate temperature variations mapped in the CMB align strikingly with patterns predicted by quantum fluctuations magnified through inflation, affirming their role as the cradles of cosmic structure. Moreover, quantum fluctuations are not relics of the past, but persist incessantly at the subatomic level. These ephemeral shifts in energy give rise to particles and antiparticles that blink into existence and vanish within instants, governed by the uncertainty principle's constraints. Though fleeting, such virtual particles exert tangible effects, manifesting in phenomena like the Casimir effect, where two uncharged metallic plates attract due to vacuum fluctuations, or the Lamb shift, a tiny adjustment in atomic energy levels measured with exceptional precision. Both phenomena underscore the profound influence of quantum fluctuations on observable physics. Beyond shaping matter and influencing experiments, quantum fluctuations fuel some of the most profound theoretical speculations in modern physics. Among them is the tantalizing hypothesis that entire universes might spontaneously emerge from these quantum ripples. Rooted in quantum cosmology, a field extending quantum mechanics to the universe as a whole, this idea intertwines with principles of general relativity and quantum theory to propose a vast multiverse, an infinite collection of universes, each potentially governed by distinct physical laws and constants. Within this framework, the inflationary theory provides fertile ground for such cosmic birth. A quantum fluctuation in a high-energy false vacuum state could trigger exponential expansion, birthing a bubble universe that rapidly inflates and evolves into a cosmos with its unique properties. This bubble could be but one among countless others, continuously spawned in an eternal, never-ending inflationary process known as the eternal inflation model, where inflation never completely halts, but endlessly produces new universes in a grand cosmic tapestry. In this breathtaking vision, quantum fluctuations are not just the seeds of our own universe, but may be the fundamental engine powering an infinite ensemble of realities. Their ceaseless dance at the edge of existence connects the infinitesimal to the infinite, weaving a narrative where vacuum energy is the silent architect of all creation, and the universe itself is but one bubble in an ever-expanding cosmic ocean. But it continues, unfolding across different regions of space-time, endlessly spawning new bubble universes. Each of these bubbles represents a nascent universe, a self-contained cosmos potentially governed by different physical constants, laws, and structures. Imagine these bubble universes as vast cosmic seeds, each sprouting its own unique reality, much like quantum fluctuations, but on an unimaginably grand scale. These ideas, though captivating, remain deeply speculative, offering only a tantalizing glimpse into the profound mysteries that arise when quantum mechanics and cosmology intertwine. Yet, despite the seductive beauty of these concepts, we must confront the limits of our understanding. Current quantum theories, while spectacularly successful at describing the behavior of particles and forces at microscopic scales, falter when asked to explain the universe's origin and the colossal phenomena that shape its vast expanse. The most glaring obstacle? The absence of a unified theory that can seamlessly marry the strange, probabilistic world of quantum mechanics with the geometric elegance of Einstein's general relativity, the theory that governs gravity. Quantum mechanics shines when describing how particles interact via the electromagnetic, weak, and strong nuclear forces. However, it notoriously fails to incorporate gravity in a coherent way. This inconsistency becomes glaringly problematic in extreme environments, deep within black holes or at the very inception of the cosmos, where both quantum effects and gravity must play vital, intertwined roles. Here lies the frontier of modern physics, the search for quantum gravity, a theory that can reconcile these two pillars of nature. Moreover, testing these grand theoretical visions, such as quantum fluctuations birthing entire universes or the existence of a vast multiverse, remains an immense challenge. These ideas, though elegant on paper, exist far beyond the reach of current experimental tools. To detect or observe another universe emerging from quantum fluctuations is a feat still confined to the realm of imagination, constrained by the sheer scale and inaccessibility of such phenomena. Likewise, foundational frameworks like quantum field theory and string theory, the latter a leading candidate for a theory of everything, have yet to deliver experimental proof for many of their bold predictions about the early universe and high-energy processes. The enigma deepens with the mysteries of dark matter and dark energy, which together compose about 95% of the universe's total mass energy content. Neither fits comfortably within the standard model of particle physics, our best tool for understanding fundamental particles and their interactions. Until these quantum theories are refined or new principles discovered to accommodate these elusive cosmic ingredients, our picture of reality remains incomplete. The pursuit of quantum gravity and the hunt for empirical evidence supporting these far-reaching theoretical insights represent the cutting edge of physics today, highlighting both our current limitations and the thrilling potential for breakthroughs yet to come. Spontaneous symmetry breaking, meanwhile, stands as a cornerstone concept within particle physics and cosmology, shedding light on the universe's creation and the incredible diversity of particles that inhabit it. In essence, spontaneous symmetry breaking occurs when a system, perfectly symmetrical under certain conditions, transitions into an asymmetric state. This phenomenon is fundamentally linked to the Higgs mechanism, which explains how particles acquire mass. To grasp this, envision the early universe moments after the Big Bang. In this initial, blisteringly hot state, the cosmos likely exhibited a high degree of symmetry, with forces and fields unified in a harmonious whole. But as the universe expanded and cooled, these symmetries broke spontaneously, much like a perfectly round ball perched atop a symmetrical hill rolling down into a particular asymmetric position. At this juncture, the Higgs field, a scalar field permeating all of space, underwent spontaneous symmetry breaking, leading to the emergence of the Higgs boson. Particles interacting with this field gained mass, differentiating themselves according to the strength of their interaction. Within the framework of the Standard Model, before this breaking, fundamental particles were massless and indistinguishable under a unified force. The process introduced distinctions, giving rise to the rich particle zoo we observe today: electrons, quarks, neutrinos, each with unique masses and properties. This symmetry breaking also gave birth to distinct force carriers: massive W and Z bosons responsible for the weak nuclear force, and the massless photon for electromagnetic interactions. Beyond the Standard Model, spontaneous symmetry breaking plays a crucial role in cosmology, influencing grand unified theories and inflation models. It drives phase transitions in the early universe that ultimately sculpt the cosmic structures defining its evolution. Thus, spontaneous symmetry breaking is far more than a theoretical abstraction. It is a vital key to understanding the origins and nature of the universe itself, bridging the realms of the very small and the unimaginably vast in a profound cosmic dance. But a fundamental process lies at the very heart of the universe's grand design, weaving an invisible yet powerful thread through the fabric of reality itself: quantum fluctuations. These fleeting, restless ripples in the quantum vacuum form the bedrock beneath the complex interactions of particles that compose everything we observe and seek to understand. Over decades, a series of pivotal experiments and groundbreaking observations have illuminated this elusive realm, turning theoretical whispers into measurable truths. One of the earliest and most striking windows into the world of quantum fluctuations was opened by Hendrik Casimir in 1948. Casimir, a Dutch physicist driven by curiosity and mathematical insight, predicted a surprising phenomenon. Place two uncharged, perfectly conducting plates just a hair's breadth apart in the vacuum of space, and they will be irresistibly drawn together. This mysterious attraction, now known as the Casimir effect, arises from the very nature of the quantum vacuum, where virtual particles flicker in and out of existence. These ephemeral particles generate a subtle pressure difference between the confined space inside the plates and the boundless vacuum outside, pushing the plates toward each other. It was not until the late 1990s that Stephen Lamoureux and other experimentalists managed to confirm this prediction with extraordinary precision, transforming a purely theoretical idea into an empirical cornerstone that reshaped our understanding of empty space itself. And yet the Casimir effect is only one chapter in this unfolding story. Another vital piece of evidence lies in the phenomenon known as the Lamb shift, first measured in 1947 by Willis Lamb and Robert Rutherford. This effect involves tiny, almost imperceptible shifts in the energy levels of electrons orbiting hydrogen atoms. The source of these shifts? Interactions between the electrons and the restless sea of virtual particles spawned by quantum fluctuations. The precision with which scientists measured the Lamb shift offered compelling support for quantum electrodynamics, the quantum field theory that describes how charged particles and electromagnetic fields dance together in the subatomic world. Perhaps the most awe-inspiring connection between the quantum and cosmic realms appears in the cosmic microwave background radiation. Discovered initially by the COBE satellite in the early 1990s, and later refined by the Dummap and Planck spacecraft, this faint afterglow of the Big Bang contains a hidden message from the dawn of time. Within the subtle variations of this radiation lie the imprints of quantum fluctuations from the infant universe, magnified by a rapid expansion known as inflation. These tiny density ripples served as the seeds from which galaxies, clusters, and the vast cosmic web grew. Thus, quantum mechanics does not just govern the minuscule, it shapes the grandest architecture of all. In the high-energy frontier of particle physics, machines like the Large Hadron Collider push the boundaries of human knowledge by recreating conditions akin to the early universe. Here, quantum fluctuations are not just theoretical constructs, they become tangible influences. The spontaneous creation of virtual particles contributes to the background noise detected in experiments, providing subtle confirmations of quantum field theories that bridge the abstract with the observable. Each collision, each fleeting particle glimpse, carries the imprint of the quantum vacuum's restless dance. Though invisible to our eyes, the effects of quantum fluctuations ripple across scales, from the tiniest electron to the cosmic expanse, affirming their indispensable role in the tapestry of modern physics. Turning now to a profound and mind-bending notion, the concept of zero total energy in the universe. This idea suggests that when all forms of energy are accounted for, the sum might balance perfectly at zero. Positive energy, which we associate with matter and radiation, is counteracted by negative energy attributed to gravity. Matter, bearing mass, holds vast amounts of energy as per Einstein's iconic equation =mc squared, while photons and other radiation contribute additional positive energy. Gravity, by contrast, is fundamentally attractive. It possesses negative potential energy because pulling masses together requires work, implying the energy balance before their union is negative. When we consider the universe's colossal structures, galaxies, clusters, the cosmic web, the gravitational energy binding these masses could offset all positive energy present. This delicate balance offers a tantalizing glimpse into cosmic origins. Some cosmological models propose the universe itself emerged as a quantum fluctuation from a vacuum state, adhering to the zero-energy principle without violating conservation laws. The universe, in this view, might be the ultimate expression of a cosmic accounting trick, a boundless expanse sprung from nothing by the interplay of positive and negative energies, quantum laws, and cosmic dynamics. This grand synthesis of quantum fluctuations and cosmic structure, zero energy and particle physics, connects the infinitely small with the infinitely vast. It reveals a universe born not in defiance of physics, but because of it. A universe whose deepest secrets whisper from the quantum vacuum, waiting for us to listen. In these extraordinary scenarios, the universe appears to borrow energy from the vacuum itself, meticulously balancing the cosmic ledger with an equivalent amount of negative gravitational energy. This remarkable concept, known as the zero-energy universe hypothesis, offers a captivating window into the profound interplay of fundamental forces on a cosmic scale. It suggests that the universe, in its vast complexity, might be governed by a perfect equilibrium, a balance so precise that the total energy sums to zero. This idea doesn't just tease our imagination, it challenges our deepest understanding of reality, touching on questions about how the universe began and what fate awaits it. But what does this balance truly mean? Imagine all the positive energy in the universe, the energy locked in matter, the kinetic energy of moving particles, and the radiant energy carried by photons and other electromagnetic waves. According to Einstein's iconic equation, E=mc squared, mass itself is a reservoir of tremendous energy, and radiation continuously courses through space, fueling countless cosmic processes. If this were the entire story, the universe would be awash in positive energy, a vast sea of power driving galaxies, stars, and planets. Yet gravity, the most enigmatic of forces, adds a profound twist. Gravity is unique because its energy is considered negative. Unlike other forces, gravity pulls objects together, creating what physicists call negative gravitational potential energy. Think of it like a cosmic balancing act. When two massive bodies are pulled apart, work must be done against gravity, adding positive energy to the system. Consequently, before this separation, the system must have held an equal amount of negative potential energy to maintain the balance. Now, scale this principle up to the entire cosmos. The sum of all these gravitational interactions between stars, galaxies, and vast clusters might perfectly offset the positive energy locked in matter and radiation. This is not merely abstract speculation. The zero-energy universe model posits that the universe could have emerged from nothing, a quantum vacuum fluctuation where energy is borrowed momentarily, allowed by the uncertainty principles of quantum mechanics. In this view, the initial spark of creation was a quantum event where positive energy, matter, and radiation appeared simultaneously with negative gravitational energy, keeping the cosmic energy budget at zero. The rapid inflationary expansion of the early universe then magnified these fluctuations, stretching them into the enormous structures we observe today, all while preserving the delicate energy balance. The implications are staggering. This elegant model bridges concepts from quantum mechanics and general relativity, suggesting that the universe might not require an external energy source to come into being. Instead, it could be a self-contained system, born from the inherent properties of space, time, and the quantum vacuum. Yet this remains a hypothesis under active scientific scrutiny. Physicists continue to debate the finer details, testing how well the concept meshes with observations and theoretical frameworks. Moreover, the nature of energy conservation in the cosmos is far from straightforward. Unlike in everyday experiences, where energy transformation follows clear rules, the universe operates under the curvature of spacetime described by Einstein's general relativity. As space itself expands, it stretches the very fabric of the universe, causing phenomena like the cosmological redshift, where photons lose energy as their wavelengths lengthen. This apparent loss of energy challenges traditional views, but fits within the broader relativistic framework, where conservation laws are subtler and sometimes local rather than global. Thus, the zero-energy universe idea encapsulates a profound paradox. Despite the immense amounts of energy we observe, massive galaxies, intense radiation fields, dynamic cosmic events, the universe's total energy might still be zero. Gravity, acting as a cosmic counterweight, ensures that every positive energy contribution is matched by a negative one. This balance not only hints at the mechanisms behind the universe's birth, but also offers clues to its ultimate destiny, weaving a narrative of cosmic harmony governed by fundamental forces in an eternal dance. In the end, the exploration of this concept reflects humanity's deepest quest to understand the cosmos, not just how it looks, but how it fundamentally works. It reminds us that the universe may be far stranger and more wondrous than our everyday experience suggests, governed by elegant laws that defy intuition and invite us to explore further into the mysteries of existence itself. But intertwined with the curvature and dynamics of space-time, the story of energy conservation in the universe takes on a complexity unlike anything in everyday experience. Despite these intricacies, a profound harmony emerges within cosmological models through the captivating concept known as the zero-energy universe hypothesis. According to this bold idea, the positive energy contained within matter and radiation is perfectly offset by the negative gravitational energy, resulting in a net energy sum of zero for the entire cosmos. This balance suggests that the universe, when viewed as a closed system, obeys the principle of energy conservation, not in the simple way we learn in classical physics, but in a nuanced, almost paradoxical manner that fits seamlessly within the relativistic framework of general relativity. Furthermore, energy conservation is not just an abstract principle, but the backbone of countless cosmic phenomena that shape the universe we observe. It governs the formation of cosmic structures, influences the enigmatic behavior of black holes, and underpins the fiery hearts of stars through the laws of thermodynamics. Take nuclear fusion, for instance. Deep within stars, mass is converted into immense amounts of energy, a process beautifully aligned with the conservation principle and Einstein's revolutionary mass-energy equivalence formula, E=squared. Yet, this process also embodies the subtle adjustments needed to accommodate the ever-changing tapestry of spacetime, warped and stretched by gravity and cosmic expansion. The conservation of energy, therefore, is not simply preserved. It is woven into the universe's very fabric, guiding both theoretical insights and empirical discoveries that seek to unravel the fundamental laws shaping our cosmos. But the quantum realm offers an even more fascinating twist to this cosmic narrative. Virtual particles, those fleeting phantoms of quantum mechanics, appear and vanish spontaneously from the vacuum of space, seemingly flouting classical energy conservation. Unlike ordinary particles, which endure and can be detected directly, virtual particles exist only for unimaginably brief moments, so transient that their direct observation is impossible. Their presence is instead inferred through subtle effects on measurable physical quantities. This ephemeral dance arises from the uncertainty principle, a cornerstone of quantum mechanics formulated by Werner Heisenberg, which allows for brief fluctuations in energy within a vacuum. In essence, energy is momentarily borrowed to create these particles, but is promptly repaid, preserving the overall conservation of energy on macroscopic scales. So, how do these ghostly quantum entities connect with the grand idea of a zero-energy universe? Here the story deepens into a cosmic balancing act of exquisite elegance. The zero-energy universe hypothesis posits that the total energy content of everything in existence sums to zero when both positive and negative contributions are considered. In this delicate equilibrium, the positive energy of matter and radiation is counterbalanced by the negative energy arising from gravitational fields. Virtual particles add a subtle yet crucial layer to this picture. They emerge fleetingly from the vacuum, contributing to transient energy fluctuations that might have played a pivotal role in the universe's very birth, a spontaneous emergence from nothing, as some cosmological models propose. Thus, these quantum apparitions are not mere curiosities confined to particle physics. They are woven into the grand tapestry of cosmology, hinting at the profound mechanisms behind the universe's origin and evolution. Calculating the universe's total energy remains one of the most challenging and meticulous endeavors in modern physics, requiring an intricate blend of general relativity and quantum mechanics. Physicists begin by quantifying the energy contributions from various components: ordinary matter, radiation, dark matter, and the mysterious dark energy. Ordinary matter, the stars, planets, and galaxies that light up the cosmos, is relatively easier to measure through telescopic observations and the gravitational pull it exerts. But then there's dark matter, an elusive substance that does not emit or absorb light, yet reveals its presence through gravitational effects on visible matter and the large-scale structure of the universe. Together with dark energy, the mysterious force driving the accelerated expansion of the universe, these components make the energy accounting profoundly complex. Ultimately, this interplay of visible and invisible energies, classical and quantum realms, positive and negative contributions, paints a picture of a universe delicately balanced on the knife edge of existence. It challenges our intuitions, pushing the boundaries of physics to explore deeper questions. How did the universe come from nothing? What are the true laws governing energy and matter on the grandest scales? The zero-energy universe hypothesis, enriched by the dance of virtual particles and the warping of space-time, stands as one of the most compelling attempts to answer these questions, inviting us to look beyond the obvious and embrace the enigmatic poetry of the cosmos, but reveals its presence through the subtle yet undeniable dance of gravity across the cosmos. Scientists, piecing together this cosmic puzzle, estimate the elusive dark matter by carefully observing how galaxies spin. Their rotational speeds defy explanation without an unseen mass holding them together. Beyond individual galaxies, the mysterious hand of dark matter bends the very fabric of light itself, creating gravitational lensing effects that magnify distant celestial objects and serve as a cosmic fingerprint of its invisible presence. On an even grander scale, dark energy emerges as the enigmatic force accelerating the universe's expansion, dominating the cosmic energy ledger. Astrophysicists measure this phenomenon by scrutinizing the light from exploding stars called supernovae, whose brightness and distance reveal the universe's growth rate. Combining these observations with the cosmic microwave background radiation, the faint afterglow of the Big Bang, physicists piece together the proportion of energy attributed to dark energy. These calculations rely heavily on Einstein's general relativity, a theory that connects the curvature of spacetime with the universe's energy content, weaving geometry and energy into a cosmic tapestry. When addressing the concept of a zero-energy universe, these cosmic energies intertwine in a delicate balance. The theory suggests that the positive energy from matter and radiation could be exactly offset by the negative gravitational potential energy, resulting in a net cosmic energy sum approaching zero. This idea transcends simple arithmetic. It demands a comprehensive grasp of the forces at play, the constituents of the universe, and the very geometry of space-time itself. Yet, this elegant notion is not without its controversies. Among the primary challenges lies the difficulty in defining and measuring gravitational potential energy in an ever-expanding universe. Unlike kinetic or mass energy, gravitational energy is inherently negative and deeply dependent on spacetime's geometry, which itself fluctuates across cosmic scales. Critics argue that in an infinite, dynamic universe, maintaining an exact ledger of positive and negative energies is a theoretical quagmire, pushing the limits of current scientific understanding and technology. Another point of debate centers on the speculative elements underpinning the theory. While some interpretations of quantum mechanics support the idea that our universe may have sprung from fluctuations in a quantum vacuum, direct empirical evidence remains elusive. Moreover, the theory hinges on assumptions about dark matter and dark energy, components whose origins and properties remain shrouded in mystery. Our incomplete knowledge of these cosmic players casts shadows over the possibility of precisely achieving a zero-energy balance. Despite these hurdles, the zero-energy universe theory presents a captivating narrative that links the infinitesimally small world of quantum mechanics to the vast expanse of cosmology. Quantum theory's Heisenberg uncertainty principle allows momentary violations of energy conservation through virtual particles, pairs that spontaneously emerge and annihilate in the vacuum. This quantum jitter opens the door to the possibility that the universe itself arose from such a quantum event, where positive energy in matter and radiation balances negative gravitational energy, netting a total energy of zero. Further enriching this framework is the holographic principle, a concept born from quantum gravity theories. It proposes that all information contained within a volume of space can be encoded on its boundary, suggesting a profound connection between quantum mechanics and the universe's very architecture. This principle strengthens the idea that the universe, adhering to the zero-energy constraint, aligns naturally with the probabilistic and often counterintuitive rules of quantum mechanics, where something can indeed arise from nothing through quantum fluctuations. Thus, the zero-energy universe theory, intertwined with quantum mechanics, sketches a paradigm where the cosmos is not a miraculous anomaly, but rather a natural outcome of fundamental quantum uncertainties. The implications for our understanding of cosmic origins are profound, challenging traditional views of creation and offering a vision of the universe spontaneously emerging from a vacuum, a space that quantum physics tells us is far from empty. This perspective transforms our conception of Genesis itself, from an inexplicable beginning to a dynamic quantum event, where the interplay of forces and energies delicately balances to birth everything we see and everything we have yet to discover. But the universe is far from empty. It is alive with ceaseless fluctuating fields and particles, constantly bubbling at the quantum level. According to the zero-energy universe theory, these quantum fluctuations are not mere random blips in an empty void. They hold the profound potential to give birth to the entire cosmos. In this remarkable framework, the positive energy carried by matter perfectly balances the negative energy inherent in gravity. This balance means that the universe's total energy could be exactly zero. If this is true, then the creation of the universe from nothing does not break any fundamental laws of physics, such as the conservation of energy. This transforms the concept of cosmic birth from an inexplicable miracle into an energetically feasible event, one that arises naturally from the quantum nature of reality itself. It offers a groundbreaking alternative to the traditional cosmological model of the Big Bang singularity, which posits a unique, inexplicable initial moment with infinite density and temperature. Instead, the zero-energy hypothesis paints a picture of a universe emerging smoothly from quantum processes, sidestepping the need for a singular event marked by unfathomable conditions. This idea also represents a promising step toward unifying the often incompatible frameworks of quantum mechanics and general relativity. By weaving them into a coherent narrative, it could finally bring clarity to the mystery of how the cosmos began within the laws of physics as we understand them. Moreover, this concept influences how scientists approach the search for the universe's initial conditions. It encourages a focus on how tiny quantum fluctuations could have expanded and evolved into the vast structures, galaxies, stars, and planets that populate our observable universe today. Through this lens, the zero-energy universe becomes not just a hypothesis, but a profound way to understand the origins and fate of all that exists, elegantly bridging the microscopic quantum world and the grand cosmic scale. Within this cosmic balancing act, dark matter and dark energy play critical roles. Dark matter, although invisible and elusive because it does not interact with light, contributes a significant portion of the universe's positive energy through its gravitational influence. Its presence is inferred from phenomena such as the way galaxies spin and the bending of light around massive objects, a gravitational lensing effect. Despite its elusive nature, dark matter adds crucial mass energy to the universe's overall energy ledger. On the other side of this cosmic equation is dark energy, a far more mysterious force thought to make up about 70% of the universe's total energy density. Dark energy is believed to be responsible for the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing speed. It is characterized by a peculiar negative pressure, which in turn manifests as negative gravitational energy. Within the zero-energy framework, this negative gravitational energy provided by dark energy balances out the positive energy contributed by both ordinary matter and dark matter. When all these components, ordinary matter, dark matter, radiation, and dark energy, are accounted for, the zero-energy universe hypothesis proposes that their sum total is zero, maintaining a delicate cosmic equilibrium. Dark matter and dark energy are not mere enigmatic entities, but essential elements in this balance, crucial for explaining the universe's emergence, its continued expansion, and its sustained existence, all consistent with the fundamental laws of physics. Adding yet another layer to this fascinating picture, the mathematical universe hypothesis, proposed by cosmologist Max Tegmark, offers a bold and compelling idea. The universe is not only described by mathematics, it fundamentally is a mathematical structure. In this view, the very fabric of reality is mathematical, meaning that the universe's physical laws and properties emerge from pure mathematical existence. This hypothesis pushes us to reconsider our place within a cosmos governed not only by physical laws, but by abstract mathematical truths, further deepening our quest to understand the origin, structure, and ultimate destiny of everything around us. But what if the very fabric of reality is woven not from matter or energy alone, but from pure mathematics itself? This is the bold and captivating proposition of Max Tegmark's mathematical universe hypothesis, a theory that challenges our deepest assumptions about the cosmos. Instead of seeing math as merely a language devised by humans to describe what we observe, Tegmark suggests that mathematics is the universe. Every particle, every galaxy, every force that governs existence emerges fundamentally from mathematical structures and relationships. Imagine reality as an immense, intricate mathematical object composed of patterns, symmetries, and constants that exist independent of human minds. In this view, the universe is not just described by mathematics, it is mathematics. Physical entities and phenomena are simply manifestations or projections of these underlying mathematical truths. What we call physical reality, then, is our limited perspective on this vast, abstract mathematical realm. If this hypothesis holds, the implications are staggering. It means that uncovering the fundamental laws of physics is tantamount to discovering universal mathematical truths, immutable, eternal, and perfect. Moreover, it opens the door to a multiverse concept unlike any other, an infinite landscape of alternate universes, each governed by its own distinct set of mathematical laws. These universes could differ wildly from our own, yet remain equally real, because their existence is rooted in the same abstract mathematical fabric. This profound relationship between mathematics and reality has puzzled philosophers and scientists for centuries. Are mathematical structures human inventions or discoveries of a deeper cosmic order? Tegmark's hypothesis leans firmly toward discovery. The universe's behavior arises inevitably from mathematics itself. These abstract structures made of numbers, shapes, symmetries, and probabilities govern everything, from the tiny quantum particles studied in physics labs to the grand cosmic patterns traced by telescopes. One of the most compelling pieces of evidence for this idea is the extraordinary predictive power of mathematics in physics. Equations such as Newton's laws of motion, Einstein's theory of relativity, and Schrödinger's equation don't just approximate physical phenomena, they predict outcomes with stunning precision. This uncanny accuracy suggests that mathematics isn't just a convenient tool, it's the very language in which the universe is written. Furthermore, mathematics bridges diverse areas of physics. The same underlying equations that describe planetary orbits also govern the behaviors of electrons inside atoms, differing only in the values plugged into these formulas. Even more strikingly, the study of symmetry through group theory lies at the heart of modern particle physics. The Standard Model, which classifies elementary particles and explains their interactions, depends heavily on symmetrical mathematical operations. Its predictions, confirmed time and again by experiments, reinforce the view that the cosmos is deeply rooted in mathematical order. Mathematical structures serve as the blueprint for the universe's laws. They do not merely describe the cosmos, they underpin it, giving rise to the rich complexity we observe. From the smallest quark to the vast cosmic web, everything unfolds according to these elegant, immutable patterns. This mathematical architecture offers not only a profound explanation of why the universe behaves as it does, but also hints at realms beyond our own, realms defined by alternative mathematical realities. In the grand quest to understand existence, Tegmark's mathematical universe hypothesis challenges us to see beyond the tangible. It invites us to recognize that reality itself might be a grand mathematical symphony, eternal and infinite, waiting to be discovered through the language of numbers, patterns, and symmetry. This vision reshapes our quest for knowledge and invites us to explore not only our universe, but an endless multiverse of mathematical possibilities. But also govern the physical phenomena we observe, revealing a profound truth. The universe itself appears to be a grand mathematical tapestry. This close relationship between mathematics and reality underscores a revolutionary idea. To truly understand the cosmos at its most fundamental level is to uncover the mathematics woven into its very fabric. Whether one fully embraces the mathematical universe hypothesis or simply acknowledges its insights, it's undeniable that mathematics provides an extraordinary and powerful lens through which we interpret existence. Mathematical structures capable of forming entire universes span a vast and diverse spectrum of abstract concepts, each defining unique properties, rules, and behaviors. Take geometry, for example, the very shapes and spaces that define our reality. Classical Euclidean geometry describes the flat, familiar space of everyday life, but alongside it lies non-Euclidean geometry, hyperbolic and elliptic geometries that describe curved spaces with astonishingly different characteristics. In a universe governed by hyperbolic geometry, the familiar rules of angles and distances break down, leading to exotic cosmological phenomena. Imagine a cosmos where space itself stretches and curves in ways that might allow faster-than-light travel or gravity behaving in unfamiliar, counterintuitive ways. Such universes stretch our imagination and challenge the boundaries of physical law. Graph theory offers yet another captivating window into possible universes. Here, the universe might not be a continuous fabric, but rather a vast network, nodes connected by edges akin to a cosmic web. Each node could represent a fundamental particle or quantum state, and the edges embody their interactions. In such a universe, space-time could be quantized, discrete rather than continuous, redefining our understanding of distance, motion, and causality. The implications ripple through the foundations of physics, hinting at new ways particles interact and forces propagate. Algebraic structures, groups, rings, and fields further enrich this panorama. These mathematical frameworks define how elements combine and interact, possibly dictating the physical laws of a universe. A universe rooted in a particular group theory might exhibit unique symmetries that give rise to conservation laws or exotic particle behaviors. These structures encode the rules that govern reality at the most fundamental level, shaping everything from the smallest quantum fluctuations to the grandest cosmic dances. Topology, the study of spaces that remain invariant under continuous deformations, invites us to envision universes with wildly different shapes and connectivity. A universe shaped like a torus, a donut, could allow closed loops in spacetime, creating cyclical time models or exotic cosmological behaviors that defy our everyday intuition. The topology of the cosmos influences not just its geometry, but its very nature and destiny. Together, these examples reveal a rich and intricate tapestry of possible universes, each defined by distinct mathematical principles. Exploring these realms provides not only a deeper insight into the nature of our own universe, but also expands our horizons to appreciate the vastness of conceivable realities. The concept of a multiverse emerges naturally from these mathematical principles, with profound implications. One key realization is that the fundamental equations describing our universe do not pinpoint a single solution, but rather encompass an infinite variety of solutions. Each corresponds to a different universe, potentially with its own physical laws and constants. General relativity, for instance, allows for solutions featuring different spacetime geometries, some curved, some flat, others warped in dimensions we struggle to visualize, suggesting a cosmic landscape of possible universes. Quantum mechanics further fuels the multiverse notion, especially through the many worlds interpretation, famously proposed by Hugh Everett. According to this view, every quantum event branches off into separate non-communicating universes, like each representing different outcomes of a quantum measurement. The mathematical framework of Hilbert space, which encapsulates all possible quantum states, inherently supports this vast multiplicity of realities. Inflationary cosmology also contributes to the multiverse framework. Alan Guth's inflationary model describes a rapid, exponential expansion of spacetime that could spawn bubble or pocket universes. Different regions of space may cease inflating at different times, producing isolated universes, each with its own distinct physical constants and laws. This theory offers a mathematically grounded mechanism for a multiverse, expanding the cosmic stage to an infinite ensemble of universes. String theory, one of the most ambitious attempts to formulate a theory of everything, adds yet another layer to this tapestry. Its complex equations admit an enormous landscape of solutions, each representing a different vacuum state with unique physical constants and dimensions. This vast string landscape hints at an astronomical number of possible universes, each governed by its own laws, reinforcing the multiverse's mathematical inevitability. Far from being mere speculation, the multiverse concept arises organically from the mathematics that govern our best physical theories. It challenges our understanding of reality, suggesting that our universe might be just one thread woven into an infinite cosmic fabric. Through the lens of mathematics, we glimpse a reality far grander and more diverse than previously imagined. A multiverse born not of fantasy, but of rigorous mathematical truth, but is deeply rooted in the mathematical principles that weave through the very fabric of physics, connecting realms as diverse as general relativity, quantum mechanics, inflationary cosmology, and string theory. These disciplines reveal a breathtaking panorama of possible universes, each governed by unique laws and constants, offering a profound shift in how we understand reality itself. It suggests that the universe we call home might be only one thread in an immense mathematical tapestry, where countless other universes unfold with their own distinct rules. Max Tegmark, a visionary cosmologist, crafted an elegant framework to organize these bewildering possibilities, dividing the multiverse concept into 4 distinct levels. Each level unfolds a progressively more expansive and speculative vision of parallel universes, pushing the boundaries of our comprehension far beyond the familiar horizon. At level 1, we encounter the multiverse closest to our experience, regions of space beyond our cosmic horizon. Although light's finite speed and the universe's age limit what we can observe, space itself stretches infinitely. Here, other universes are simply distant regions where matter might arrange itself differently, giving rise to alternate cosmic structures and histories, all operating under the same physical laws and constants that govern our own. These universes are not separated by new laws, but by unimaginable distances within an endless cosmos. Level 2 ventures deeper into the extraordinary, born from the theory of eternal inflation. Unlike the singular explosive birth of our universe, eternal inflation proposes that space is perpetually expanding, spawning countless pocket universes in a grand cosmic garden. Each pocket can manifest different physical constants, particles, or even extra dimensions, shaped by how symmetry breaking unfolds during inflation. This process creates a wildly diverse multiverse, where each universe might abide by laws radically different from our own. Delving further into abstraction, level 3 arises from the many worlds interpretation of quantum mechanics. Here, every quantum event doesn't just have one outcome. It simultaneously spawns all possible outcomes, each in its own branch of reality. This multiverse isn't about distant regions of space, but parallel realities existing side by side, born from the collapse of the quantum wave function into every conceivable possibility. It's a dizzying idea, an ever-branching tree of universes where every choice, every chance event births a new world. The final and most speculative is level 4, which pushes the concept of reality itself to the brink. Tegmark proposes that all mathematical structures exist physically, that mathematics is not merely a language to describe reality, but the very substance of reality itself. According to this view, every mathematically consistent universe exists, each with its own foundational rules and definitions. This level encompasses the entirety of conceivable universes described by any mathematical framework, presenting an infinite and all-encompassing multiverse that defies the limits of imagination. Tegmark's 4 levels offer not just a roadmap, but a profound lens through which to explore the nature of existence. They shift our perspective from thinking of the universe as a singular, isolated domain to recognizing a cosmic landscape filled with countless realities, each as valid as our own. This journey challenges both science and philosophy, inviting us to reconsider what universe truly means. Central to this exploration is the concept of symmetry, a foundational principle in mathematics and physics. Symmetry is the idea that certain properties remain unchanged under transformations like rotations, reflections, or translations. But in the mathematical multiverse, symmetry transcends mere elegance or simplification. It becomes a cornerstone that shapes the very laws and constants defining each universe. From the spinning galaxies to the behavior of fundamental particles, symmetrical patterns guide the structures and behaviors that emerge across the multiverse, linking abstract mathematics to tangible reality in ways we are only beginning to grasp. This documentary journey into the multiverse reveals a cosmos far more intricate and vast than previously imagined. A cosmos where mathematics and physics converge to suggest a stunning reality filled with infinite possibilities, beckoning us to explore what lies beyond the known, to venture into the uncharted realms of existence itself, but are deeply embedded in the very fabric of the physical world and the mathematical structures that define what we call the multiverse. Symmetry is not just a vague idea, it is the invisible hand that guides the fundamental laws and constants shaping each universe within this vast mathematical landscape. Take, for instance, the standard model of particle physics, our best description of the forces and particles that govern reality here. This model is built upon intricate symmetrical properties, beautifully described through the language of group theory. These symmetries dictate how particles interact, guaranteeing the conservation of essential quantities like energy, momentum, and electric charge, the cornerstones of stability in any universe. Different universes within this mathematical multiverse may arise from distinct symmetry groups, each prescribing unique sets of physical laws and constants. Imagine a universe governed by an alternate symmetry group, where the fundamental particles differ, or where forces act in ways completely alien to us. Such a universe would possess physical properties beyond our wildest imagination, each shaped by its own symmetrical blueprint. Moreover, the phenomenon of symmetry breaking plays a crucial role in the diversification of these universes. Symmetry breaking occurs when a system that initially exhibits perfect symmetry shifts into a state of lower symmetry under specific conditions. In cosmology, this is no mere abstraction. During the early moments after the Big Bang, spontaneous symmetry breaking transformed the universe from a uniform, high-symmetry state into one filled with the complex structures and distinct forces we observe today. The 4 fundamental forces, Gravity, electromagnetism, and the strong and weak nuclear forces are thought to have once been unified, only to split apart through such symmetry-breaking events. Different patterns or instances of symmetry breaking in other universes could give rise to entirely different physical realities, each with its own laws and constants, crafting a cosmic mosaic of infinite variety. At an even deeper, more abstract level, the mathematical structures underpinning Max Tegmark's Level 4 multiverse are themselves inherently symmetrical. These abstract structures possess intrinsic symmetries that define their fundamental properties and behaviors. For example, geometric spaces exhibit symmetries such as rotational and translational invariance, leading to diverse spatial geometries. Within a multiverse composed of these varying mathematical frameworks, the unique symmetries of each structure determine the very nature of the universe it corresponds to. Symmetry also serves as a bridge, uniting disparate physical phenomena under a coherent mathematical framework. Emmy Noether's theorem stands as one of theoretical physics' crowning achievements, linking symmetries directly to conservation laws. This profound principle implies that even across the dizzying diversity of universes in the mathematical multiverse, universal symmetrical laws may prevail, realized in countless different ways but echoing a deeper harmony. Thus, symmetry in the mathematical multiverse transcends being a mere conceptual tool. It is a foundational principle shaping the properties, behaviors, and laws governing each individual universe. Different symmetry groups and symmetry-breaking events sow the seeds of the astonishing diversity that the multiverse holds, each universe a distinct mathematical tapestry woven from consistent and elegant rules. The profound relationship between mathematics and physical laws lies at the heart of this cosmic order. Mathematics provides not only the language, but the very framework through which we understand and articulate the universe. It acts as the bridge between abstract theoretical constructs and empirical reality, enabling us to grasp the laws that govern everything from subatomic particles to galactic clusters. One of the most compelling aspects of this relationship is mathematics' predictive power. Physical laws, expressed through precise mathematical formulas, allow us to forecast the behavior of natural systems with remarkable accuracy. Newton's laws of motion and universal gravitation, articulated in elegant equations, can predict the trajectories of planets and falling objects alike. Einstein's general relativity, encapsulated in the field equations describing space-time curvature, predicted phenomena such as gravitational lensing and the universe's expansion, observations later confirmed by experiment. Moreover, mathematics offers a unifying framework linking seemingly unrelated physical phenomena. Maxwell's equations, for instance, merge electricity and magnetism into a single cohesive theory of electromagnetism. In the quantum realm, Schrödinger's equation governs the probabilistic nature of particles at microscopic scales, introducing wave functions that describe reality's fundamental fuzziness. The inherent symmetry underlying many physical laws is fundamentally mathematical. Group theory, the study of symmetrical structures, forms the backbone of modern physics. It underpins the Standard Model explaining the connections among forces and particles. Emmy Noether's theorem formalizes this link, tying physical invariances to conservation laws like energy and momentum conservation, revealing a deep connection between nature's constants and mathematical symmetry. This relationship extends even further into the frontiers of theoretical physics. Concepts such as string theory rely heavily on advanced mathematics, proposing that fundamental particles are not mere points, but tiny vibrating strings whose modes correspond to particle types. This theory's mathematical elegance hinges on symmetrical properties in higher dimensional spaces, offering a tantalizing glimpse into a unified description of all forces. In the grand tapestry of the mathematical multiverse, symmetry is not simply an aesthetic ideal. It is the underlying principle weaving together the fabric of countless universes. Through the interplay of symmetrical laws and their breaking, the cosmos unfolds in an infinite variety of forms, each governed by mathematical consistency and profound order. This symphony of symmetry invites us to glimpse the profound unity behind the staggering diversity of existence itself. But rather one-dimensional strings whose vibrations at the quantum level dictate the fundamental properties of particles. These strings do not simply exist in our familiar three-dimensional space, but instead operate within higher dimensional realms, invoking intricate mathematical frameworks such as differential geometry and topology to describe phenomena that stretch the limits of human comprehension. These advanced mathematical tools enable scientists to explore cosmological and quantum mysteries, forging connections that reveal the universe's underlying order. The fascinating aspect of this interplay is that mathematical discoveries often precede their physical application, a recurring pattern throughout scientific history. Non-Euclidean geometries, once purely abstract mathematical constructs, found profound physical significance in Einstein's theory of general relativity, which showed that space-time itself is curved. This remarkable revelation emerged decades after mathematicians first developed these concepts, without any notion of their real-world utility. Such instances suggest that mathematics is not merely a human invention, but possesses an intrinsic ability to uncover the fabric of reality, often predicting scientific breakthroughs long before experimental evidence confirms them. The relationship between mathematics and physics is more than collaborative, it is symbiotic. Mathematics offers the essential language to articulate the laws governing the natural world, allowing physicists to formulate precise equations that predict cosmic events and unify seemingly disparate phenomena. Whether describing the forces that govern motion or constructing abstract frameworks like string theory, mathematics serves as the foundation upon which modern physics is built. This profound connection hints at a universe that may, at its core, be fundamentally mathematical, a concept that fuels many of today's most speculative scientific theories. Diving deeper, different mathematical models can produce entirely distinct universes by defining alternate sets of physical laws, constants, and parameters. These variations shape the possibilities of how a universe can evolve, behave, and even exist. Each model encapsulates a unique framework of rules, influencing everything from the nature of particles to the grand architecture of space-time itself. This notion leads to the intriguing concept of a multiverse, a vast ensemble of universes each governed by mathematical realities. Consider the role of geometry, for example. The very nature of space, whether it is flat, hyperbolic, or spherical, determines how matter and energy interact. Our universe's geometry, described by Riemannian geometry, allows for the curvature of space-time, explaining gravity's behavior. However, if the universe were governed by a different geometric structure with alternate curvature or dimensionality, its gravitational dynamics would change, potentially resulting in drastically different cosmic landscapes, from star formation to black hole behavior. Quantum mechanics further illustrates this diversity. The Schrödinger equation predicts the probabilities of quantum events, but alternative formulations, such as the pilot wave theory or objective collapse models, envision universes where quantum phenomena unfold in radically different ways. Such differences could alter atomic structures and fundamentally change the nature of randomness, determinism, and the very fabric of reality. Symmetry plays a critical role too. The standard model of particle physics depends on specific symmetry groups like SU3 to SU1 to explain particle interactions. If these symmetry groups varied, the fundamental particles and forces would also differ, reshaping the laws of physics and resulting in universes with unfamiliar physical phenomena and constants. Different gauge groups might introduce new forces or alter particle properties in ways that challenge our understanding of matter. Mathematical constants, such as the gravitational constant, the speed of light, and Planck's constant, define the behavior of physical systems. Even small variations in these values could radically change star formation, planetary orbits, and cosmic evolution. For instance, a universe with a slightly different gravitational constant might see vastly altered cosmic structures or expansion rates, illustrating how sensitive the cosmos is to these fundamental parameters. String theory expands this vision further by proposing an immense landscape of possible universes, each represented by different configurations of strings, branes, and compactified dimensions. These solutions, known as vacua, yield distinct sets of physical laws and constants, suggesting an almost infinite array of possible realities. This mathematical multiverse challenges our traditional notions of existence. Reality, once confined to the observable cosmos, now potentially encompasses every conceivable mathematical structure. If each such structure corresponds to a universe, then the domain of what is real extends far beyond human observation, reshaping the very definition of existence and inviting us to reconsider our place in an unimaginably vast and varied cosmos. But a vast expanse unfolds beyond our familiar cosmos, a collection of universes as real as our own, each governed by its own distinct mathematical laws and principles. This bold vision shakes the very foundations of ontology, urging us to embrace a pluralistic view of existence. No longer confined to a singular reality, we are invited to consider a multiverse, rich with diversity, where countless realities coexist, each shaped by its unique rules. And yet, this vision raises profound questions about the limits of human understanding. If there truly are infinite universes, each with its own physical laws and constants, then comprehending our own universe becomes a humble local endeavor, a mere glimpse within an unfathomably vast and possibly unknowable framework. The quest for knowledge, so central to scientific inquiry, is called into question. Are there universal truths that apply across all these realities, or are our scientific laws simply one particular set among infinite possibilities? This challenges the long-held assumption of uniqueness in the laws we discover, suggesting instead that they might be contingent reflections of our own mathematical vantage point. Moreover, the idea of a mathematical multiverse offers a fresh perspective on the intriguing phenomenon known as fine-tuning. The fine-tuning argument points to the precise calibration of constants in our universe that allow life, particularly intelligent life, to emerge and thrive. But if every conceivable mathematical universe exists somewhere in the multiverse, then the existence of a life-permitting universe is not extraordinary, but inevitable. In this immense diversity, our cosmos is no longer a rare jewel requiring design, but a natural product of infinite variation. This shift transforms a debate rooted in design into one grounded in cosmic abundance. Ethically and existentially, this multiverse perspective both humbles and liberates us. It humbles by revealing that our universe, and indeed our lives, may be just one among uncountable others, diminishing the sense of cosmic singularity. Yet it also liberates by affirming that every possibility, every path of existence is realized somewhere in this grand multiversal tapestry. In a sense, this view offers a cosmic freedom. If our story is but one thread, the entire fabric is rich with endless narratives. The mathematical multiverse also resonates deeply with the philosophy of mathematics, particularly mathematical Platonism, the idea that mathematical entities exist independently of human minds. If every mathematical structure corresponds to a physical universe, then abstract mathematics transcends mere human invention. It becomes an intrinsic part of the cosmos itself. This suggests that mathematical discovery is not mere creativity, but the uncovering of fundamental truths embedded in the multiversal reality. Imagine then that our universe is only one among countless mathematical structures, each self-contained and ruled by its own internal logic. This is the core of cosmologist Max Tegmark's mathematical universe hypothesis, proposing that these structures exist in a Platonic realm, eternal and immutable. The true wonder emerges when we consider: if each universe is isolated by its unique laws, could they ever interact? Some theorists speculate that a phenomenon analogous to quantum entanglement, where particles remain mysteriously linked across vast distances, might apply at a multiversal scale. Such entanglement would not imply direct exchanges of matter or energy, but a subtler interplay of information or influence, weaving these separate realms into a hidden cosmic web. If such inter-universal interactions exist, they would revolutionize our understanding of reality, unveiling a meta-reality where different universes form an interconnected cosmic fabric far beyond our current grasp. This cosmic mystery ties intimately to one of the most compelling arguments for the existence of a divine creator: the fine-tuning of the universe. Observers note that fundamental constants, such as the gravitational constant, electromagnetic strength, and the universe's expansion rate, appear extraordinarily precise, seemingly calibrated to permit the emergence of life. If even slight deviations occurred, stars might never ignite, and life as we know it would be impossible. This exquisite precision provokes profound questions. Are these constants mere cosmic happenstance, or are they the signature of an intelligent designer? For many, the near impossibility of chance births a conviction that such delicate balance points to a higher intelligence orchestrating the cosmos. Yet, within the mathematical multiverse framework, this fine-tuning need not imply intentional design. Instead, it may be the natural outcome of infinite universes, where some naturally harbor conditions ripe for life. Whether this view diminishes or deepens the mystery remains an open question, a testament to the profound and awe-inspiring quest to understand our place within the vast tapestry of existence. But necessary, another major argument is the cosmological argument, particularly the Kalam cosmological argument, which hinges on the principle of causality. This profound philosophical position asserts that everything that begins to exist must have a cause. Applying this principle to the universe itself, which, according to modern science, began with the Big Bang around 13.8 billion years ago, leads to a fascinating and unavoidable conclusion. The universe cannot be the exception to this rule. It, too, must have a cause. This line of reasoning invites us to consider a cause that exists beyond the familiar dimensions of space and time, something utterly transcendent and foundational. For many, this cause is best understood as a divine creator, an entity possessing the extraordinary power not only to bring matter into existence, but to fashion the very fabric of space-time itself. This is not merely a scientific or metaphysical abstraction, but a concept deeply rooted in centuries of philosophical thought. The argument intertwines elegantly with the musings of great thinkers like Aristotle and Aquinas, who contemplated the necessity of a first mover, or necessary being. They reasoned that without such a prime cause, the continuous existence and motion of everything we observe would be inexplicable, a concept that still resonates strongly in contemporary theological discourse. In Christianity, the creation of the universe is more than an abstract concept. It is a central narrative, vividly depicted in the book of Genesis. Here, the Judeo-Christian tradition unfolds a dramatic sequence. God creates the heavens and the earth in 6 days, resting on the seventh. This creation narrative moves with deliberate purpose and poetic order. First, light is called into being, separated from darkness. The sky, land, and seas are formed. Plants and animals fill the earth, and finally, humans are created. The story reflects an omnipotent and benevolent creator who acts with intentionality and power, establishing not only the physical world, but an ordered, meaningful cosmos. Yet, the Genesis account invites multiple interpretations. While some hold it as a literal historical record, others approach it allegorically, by recognizing it as a symbolic narrative that conveys profound truths about the divine origin of the cosmos. It speaks to the inherent order of life and humanity's special role within creation, suggesting a relationship between the creator and creation that transcends mere material existence. Turning to Hinduism, the vision of creation is strikingly different, emphasizing a cyclical rather than linear understanding of cosmic existence. According to Hindu cosmology, the universe undergoes endless cycles of creation, preservation, and destruction, known as yugas. These grand cosmic rhythms are presided over by a triad of gods: Brahma, the creator, Vishnu, the preserver, and Shiva, the destroyer. This triadic process symbolizes the dynamic flow of the universe through phases of birth, maintenance, and dissolution, a perpetual dance of cosmic forces. Ancient Hindu texts like the Rig Veda explore these themes through evocative imagery. One of the oldest hymns describes a primordial cosmic being, Purusha, whose self-sacrifice becomes the source of all creation. Other myths tell of the gods and demons churning the cosmic ocean to produce the nectar of immortality, revealing a rich symbolic tapestry of the universe's origins that is both mystical and profound. Across many religious traditions, including Islam and Buddhism, creation stories serve as windows into how different cultures conceptualize the cosmos, humanity's place within it, and the divine or metaphysical powers that govern existence. The Quran, for example, depicts the universe as created by Allah in a systematic unfolding, from a state of formless darkness to an ordered world, emphasizing divine omnipotence and unity. Conversely, Buddhist cosmology does not center on a creator deity, but rather on endless cycles shaped by karma and cosmic law, reflecting a worldview in which the universe is an eternal, dynamic process without a definitive beginning or end. Each perspective offers a unique lens for believers to understand existence, the nature of the universe, and the metaphysical realities that sustain life itself. The cosmological argument, particularly the notion of a first cause, emerges from centuries of deep philosophical and theological reflection. It posits that if every effect has a cause, then tracing these causes back logically requires a starting point, a first cause that itself is uncaused, an ultimate source setting all things into motion. This uncaused cause is often identified with a divine creator or prime mover, a concept famously articulated by Aristotle. He introduced the idea of an unmoved mover, a perfect being whose very existence explains all movement and change in the universe. For Aristotle, the cosmos could not be infinite in regress. Rather, it demanded a foundational cause that itself remains unmoved, eternal, and necessary. This profound insight has influenced not only medieval theologians like Aquinas, but also modern philosophical and theological thought, anchoring the cosmological argument as one of the most enduring and compelling proofs for the existence of a transcendent origin behind everything we see. This mover is eternal, unchanging, and fully actualized, meaning it possesses no potential for change because it is already perfect in its entirety. This profound concept, rooted in classical philosophy, was elaborated by Thomas Aquinas, who built upon Aristotle's foundational ideas. Aquinas formulated his famous 5 ways within the Summa Theologica, a monumental work where he argued that the chain of causes cannot stretch back infinitely. It must logically culminate in a first cause, universally understood as God. Aquinas' reasoning rests on the impossibility of an infinite regress of causes. Without a first cause to initiate the sequence, nothing could exist at all in the present moment. Yet this notion of an originating cause is not confined solely to Western philosophy. Across diverse cultures and religions, from east to west, there is a recognition of an ultimate source or principle that sparks existence itself. While monotheistic traditions personify this source as God, various Eastern philosophies conceptualize it more abstractly. For instance, Hinduism venerates Brahman, the ultimate reality or cosmic spirit from which the universe emanates. In certain interpretations of Buddhism, the intricate web of causality implies the necessity of an underlying source or foundation, even if it is not personalized as a deity. The dialogue between these ancient metaphysical ideas and modern science adds further richness to the concept of a first cause. Contemporary cosmology, particularly the Big Bang Theory, describes a profound event around 13.8 billion years ago, when all space, time, and matter exploded outward from an incredibly hot and dense singularity. Many scholars and theologians see this cosmic origin as a point hinting at the presence of a first cause. Others caution that the physics at that singularity remains mysterious and incomplete, leaving open questions about what, if anything, preceded it. Whether approached through the lenses of religion, philosophy, or science, the question of the universe's ultimate origin remains a powerful catalyst for deep reflection and vigorous debate. At the heart of this inquiry lies the cosmological argument, a classical philosophical and theological rationale for the existence of a divine creator. This argument fundamentally depends on the principle of causality. Every effect must have a cause. Since the universe exists as an effect, the argument concludes it must ultimately trace back to a cause that itself is uncaused, an unconditioned origin often identified as God. One of the most well-known expressions of this reasoning can be framed simply: everything that begins to exist has a cause. The universe began to exist. Therefore, the universe must have a cause. The persuasive strength of this argument stems from its logical flow, particularly when supported by empirical findings like the Big Bang. Because the universe encompasses all space and time, this primal cause must exist beyond those dimensions, immaterial, timeless, and possessing immense power, attributes traditionally associated with the divine. Another powerful variation is Aquinas' argument from contingency. Aquinas observed that all things in the universe are contingent. They exist, but they could conceivably not exist. Their existence depends on external factors. If everything were contingent, there could have been a time when nothing existed at all. Since nothing can come from nothing, there must be at least one necessary being whose existence is not dependent on anything else but is inherent and eternal. This necessary being, which grounds the reality of all contingent things, is identified with God. Together, these arguments weave a compelling case for a divine creator. They emphasize the necessity of a first cause or an unconditioned reality that accounts for the very existence and nature of everything within the universe. The assertion is that the universe's existence is most coherently explained by the presence of a divine creator, an originator who initiates, sustains, and governs all being and becoming. Adding another layer to this discussion is the fine-tuning argument for a supreme creator. It points out that the universe's fundamental conditions necessary for life are astonishingly precise, so improbably exact that they suggest intentional design. Consider the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each operates within an extraordinarily narrow range that allows for the emergence of life. Even the slightest deviation would render the universe inhospitable. This meticulous calibration raises the profound possibility that a purposeful creator set these conditions deliberately, with the intent of fostering life and complexity. While some argue this precision might be explained through chance or multiverse theories, others see in it a testament to a cosmic intelligence behind existence. In sum, the quest to understand the origin of the universe, whether through philosophical reasoning, theological insight, or scientific discovery, continues to captivate humanity. It calls us to confront the mystery of existence itself, inviting us to explore what lies beyond the cosmos and to ponder the timeless question: what caused everything to be? In this fascinating exploration of the cosmos, we dive into a mind-boggling concept that has intrigued scientists, philosophers, and theologians alike: the fine-tuning of the universe. Imagine for a moment that the fundamental constants of nature, such as the strength of gravity or the forces governing subatomic particles, were even slightly different. If the gravitational constant, for instance, were just a bit stronger or weaker, the universe could have collapsed upon itself in an instant, or expanded too rapidly for galaxies, stars, and planets to ever form. This delicate balance is not confined to gravity alone. It extends to the fine-tuning of the strong and weak nuclear forces, which govern the behavior of atomic nuclei and are critical in the formation of the basic elements necessary for life itself. These parameters, among dozens of others, are so precisely set that the very existence of life as we know it seems improbable by any statistical measure. The odds of these values aligning to create a universe capable of supporting life are so slim that they can only be compared to winning a lottery, an extremely rare event. For those who advocate the fine-tuning argument, this apparent cosmic precision strongly suggests that the universe was designed with life in mind. Supporters argue that such a highly improbable outcome is not likely to have occurred by mere chance, and thus they propose the idea of an intelligent designer who meticulously set the laws of the universe to allow life to emerge. This designer is often depicted as a supreme being, one who purposefully calibrated the universe's laws and constants. One of the most prominent proponents of this idea, physicist John Polkinghorne, contends that the elegance and order found in the mathematical laws of physics point to the work of a mind behind the cosmos. This sense of order, he argues, cannot be reduced to random chance or impersonal forces alone. Similarly, philosopher Robin Collins has made a compelling case for the fine-tuning argument, suggesting that it significantly strengthens the case for a divine creator, one who deliberately designed the universe with life in mind. According to Collins, the improbable nature of life-sustaining conditions is not just a curiosity, it's a sign of intentionality, a deliberate act by a creator who crafted the universe with a specific purpose. Of course, there are alternative explanations. One of the most popular competing theories is the multiverse hypothesis, which posits that there are countless other universes, each with its own set of laws and constants. In this view, our universe just happens to be one in which the conditions are right for life. However, proponents of the fine-tuning argument maintain that the idea of a divine creator remains the most plausible and elegant solution to the mystery of our life-permitting universe. They argue that the idea of an intelligent, purposeful creator is not only a simpler explanation, but also one that resonates more deeply with the nature of existence itself. The question of how to reconcile scientific theories with the belief in a divine creator has led to a variety of frameworks that emphasize compatibility rather than conflict. One such framework is the concept of theistic evolution, which proposes that the processes of biological evolution, as described by science, are the means through which a divine creator brought about life. This perspective allows for the acceptance of evolutionary theory and the vast timescales of geology, viewing them not as contradictory to divine action, but rather as expressions of it. In this view, the natural processes uncovered by science are not seen as separate from the divine, but as mechanisms that serve the creator's purpose. Prominent figures in both science and theology, such as Polkinghorne and Francis Collins, advocate for this approach, suggesting that science and religion are not at odds, but rather address different dimensions of the same reality. Polkinghorne, for example, uses the term complementarity to describe how science and religion each offer a unique perspective on the truth. While science uncovers the mechanisms behind the universe, such as the Big Bang theory or evolutionary processes, religion addresses the deeper questions of meaning and purpose. This approach doesn't seek to fill gaps in scientific knowledge with divine intervention, but rather to acknowledge the divine hand in the known processes of the universe. Another approach that seeks to reconcile scientific understanding with faith is the interpretative flexibility of sacred texts. Many theologians argue that the creation narratives found in sacred scriptures, such as the book of Genesis, should be understood not in a literal sense, but as allegories or metaphors. For example, the 6 days of creation might be seen as symbolic of much longer periods of time, aligning with the scientific understanding that the universe is approximately 13.8 billion years old. This metaphorical interpretation allows believers to uphold the theological truths of creation, such as the belief in a purposeful, divinely guided origin of the universe, while also embracing the findings of modern science. Moreover, the principle of contingency offers a profound synthesis between divine creation and scientific discovery. The principle holds that the laws of nature and the constants of the universe could have been otherwise. This opens the door to the question of why the universe is configured in such a way that life is possible. From a theological standpoint, the contingent nature of the universe points to a divine creator who made deliberate choices in creating a life-permitting cosmos. This suggests a purposeful act of creation that aligns harmoniously with scientific understanding, which speaks to the universe's constitution and history. Through these various approaches, theologians and scientists alike seek to build a coherent worldview that integrates both the empirical rigor of science and the spiritual insights of theology. This integrated perspective enriches our understanding of the universe by acknowledging both divine purpose and natural processes. While philosophical objections to the existence of a divine creator remain, particularly those raised by the problem of evil, the pursuit of a comprehensive understanding of the universe continues to evolve, shaping both our scientific knowledge and our spiritual beliefs. Ultimately, the question of whether the universe is the product of chance or design is one that beckons us to explore the profound mysteries of existence, offering a glimpse into the intricate, awe-inspiring order that governs all things. But chooses not to. It raises significant doubts about either the nature or even the very existence of such a being. The world around us is filled with profound suffering and pervasive evils, both natural disasters and moral failings, that challenge the traditional attributes often ascribed to a divine creator. The question arises, how can an all-powerful, all-knowing, and all-good deity permit such pervasive pain and injustice? This dilemma stands as one of the most persistent and perplexing in the history of philosophy and theology. And yet, the problem deepens when we consider the insights of empiricism and the principle of parsimony, often associated with the Scottish philosopher David Hume and later refined as Occam's razor. This principle guides us to prefer simpler explanations that do not multiply assumptions unnecessarily. Many modern philosophers and scientists argue that naturalistic explanations, grounded in observable phenomena and rigorous scientific methods, provide clearer and more straightforward accounts of the universe's origins and mechanisms. Invoking a supernatural divine creator, they claim, adds unnecessary layers of complexity without offering explanatory benefits beyond what empirical science has already uncovered. Moreover, the cosmological argument, which seeks to establish God as the first cause of everything, encounters a thorny problem: the issue of infinite regress. If every effect requires a cause, then what caused the divine creator? Critics assert that positing God as an uncaused cause merely pushes the question further back without resolving it. This leads to a logical puzzle. Either everything must have a cause, or something must exist without a cause, a special pleading that many skeptics view as a conceptual weakness, undermining the argument's strength. But the critique does not end there. From the vantage point of non-theistic existentialism, championed by philosophers like Jean-Paul Sartre and Friedrich Nietzsche, the very necessity and desirability of a divine creator are called into question. Sartre, for instance, passionately argued that human beings must forge their own purpose and meaning through their choices, actions, and relationships. This view promotes an autonomy of existence where meaning is not granted by an external deity, but created by the individual. Such a stance often conflicts with traditional theistic views that posit a predetermined, divinely ordained purpose for human life. Together, these diverse philosophical objections weave a complex tapestry of doubt and inquiry, questioning the coherence, necessity, and implications of a divine creator. They fuel ongoing debates within both philosophical and theological circles, pushing thinkers to explore new avenues and refine old arguments. The problem of evil remains one of the most formidable challenges confronting theistic belief. How could a God who is omnipotent, omniscient, and wholly good allow evil and suffering to persist in the world? This problem presents itself both logically and evidentially, each form offering deep critiques of theistic claims. The logical problem, famously articulated by Epicurus and later refined by J.L. Mackie, posits a contradiction. If God is all-powerful, he could eliminate evil. If he is all-knowing, he would know about all evil. And if he is all-good, he would desire to eradicate evil. Yet evil undeniably exists, seemingly undermining the coherence of such a God. In response, many theists turn to the free will defense, notably advanced by Alvin Plantinga. This defense suggests that God grants human beings free will, a precious and greater good that justifies the possibility of moral evil. Free will allows for genuine relationships and moral growth, permitting humans to choose good or evil freely. While this defense addresses the existence of moral evil, it leaves open questions about natural evil, suffering caused by natural events rather than human choice, continuing to challenge theologians and philosophers alike. Thus, the exploration of these profound philosophical dilemmas continues, revealing the depth and complexity inherent in understanding the divine, the origins of the universe, and the nature of good and evil. But it also permits individuals to choose evil actions, thus opening a profound window into one of humanity's oldest and most intricate dilemmas: the coexistence of free will and evil in a world fashioned by a divine creator. This paradox challenges the heart of theological and philosophical thought. How can a benevolent, all-powerful, and all-knowing God allow evil to exist? The existence of evil in this framework emerges not as a flaw in divine design, but as an inevitable consequence of granting humanity freedom. This freedom to choose, a gift of immense responsibility, inevitably includes the potential to choose wrong. The evidential problem of evil, advanced by thinkers like William Rowe, dives deeper into this debate. Instead of asserting a strict logical contradiction, it questions the probability that an omnipotent and omnibenevolent God would permit the staggering magnitude of suffering observed in the world. This argument highlights instances of intense and seemingly pointless suffering, natural disasters devastating communities, innocent children enduring unimaginable pain, and posits that such gratuitous suffering appears incompatible with a world governed by a perfectly good deity. The weight of this evidence challenges the likelihood, if not the logical possibility, of such a divine presence. In the quest to reconcile these troubling observations, some theologians turn to the concept of soul-making, a theodicy articulated by John Hick. According to this perspective, the hardships and trials of the world are not mere cruelties, but necessary crucibles for spiritual and moral growth. The suffering one endures is a forge for character, a pathway toward higher moral and collective development that ultimately aligns with divine purposes. Though these divine intentions may be obscured from human understanding, the soul-making theodicy suggests that the painful episodes in life serve a greater formative role, shaping individuals and communities into beings capable of deeper goodness and virtue. Complementing this is the perspective of skeptical theism, which acknowledges human epistemic limits. From this vantage, what we perceive as gratuitous suffering might be woven into a larger tapestry of meaning and purpose beyond our grasp. Trusting in the divine wisdom and benevolence becomes a rational stance, even in the face of profound mystery. Skeptical theism invites humility, reminding us that human knowledge is limited, and that divine reasons may remain forever beyond our comprehension. Thus, the problem of evil is not resolved by simple answers, but remains a fertile ground for profound philosophical and theological inquiry into the nature of divinity, free will, moral growth, and the boundaries of human understanding. This timeless struggle to understand creation, suffering, and divine purpose resonates not only in modern debates, but also echoes through the creation myths of cultures worldwide. These stories offer us glimpses into humanity's universal quest to explain existence, each culture weaving narratives imbued with symbolism and insight, shaped by their unique experiences and environments. In the Judeo-Christian tradition, as recounted in the book of Genesis, the universe unfolds through the deliberate acts of a singular omnipotent God over 6 days. Each phase of creation, from the genesis of light to the formation of humans, reflects a deliberate and purposeful unfolding of the cosmos, culminating in a day of rest that sanctifies the process. This narrative frames creation as an intentional, benevolent act by a personal deity, setting the foundation for Abrahamic faiths and underscoring themes of order, goodness, and divine intentionality. Contrast this with Chinese cosmological narratives such as the myth of Pangu, where the universe is born from the cosmic egg. Pangu's own transformation, his separation of chaos into heaven and earth, and his death giving rise to natural elements, embodies a deeply animistic worldview. The myth portrays the universe as an interconnected living organism, emphasizing unity and the intimate bond between creator and creation. Here, creation is a physical and spiritual transformation, underscoring a holistic interdependence between all things. Moving to the Polynesian world, the Hawaiian creation chant Kumulipo offers yet another vibrant vision. This genealogical prayer traces the cosmic origins through generations, revealing a universe born from primordial darkness and unfolding life forms. It stresses the interconnectedness of gods, nature, and humanity, portraying creation as an ongoing, evolving story where all beings share common ancestry and destiny, underscoring the sacred unity of life. Similarly rich is the Hindu creation account from the Rig Veda. It recounts the cosmic sacrifice of Purusa, a primordial being whose dismemberment leads to the formation of the universe's various elements, deities, and social orders. This myth articulates a cyclical view of existence, creation, preservation, and destruction, as eternal rhythms that define reality. The sacrificial act speaks to themes of unity and transformation, deeply embedded in Hindu metaphysics and spirituality. Indigenous American traditions, such as the Navajo creation story, present creation as a communal journey. Ancestors traverse multiple worlds, each stage marking spiritual and physical development. This narrative celebrates transformation and collective effort, portraying existence as a process sustained by community cooperation and harmony with the natural and spiritual realms. In stark contrast, the Nordic myth of creation springs from conflict and elemental forces. The icy void Ginnungagap, where fire meets ice, births the primordial giant Ymir. From Ymir's body, Odin and his brothers forged the world. This myth reflects themes of struggle, transformation through conflict, and the balancing of opposing forces, revealing a cosmos shaped through dynamic tension rather than peaceful order. Despite their differences, these creation myths share striking thematic threads: the movement from chaos to order, the importance of sacrifice, the interplay of elemental forces, and the intimate ties binding the divine to humanity. These narratives, rich with symbolism, reveal how diverse human cultures have grappled with fundamental questions about existence, purpose, and the sacred. Faith remains a central pillar in interpreting these origins, serving as a bridge between the known and the unknowable. Unlike scientific inquiry, which relies on empirical evidence and reproducibility, faith embraces truths beyond immediate sensory experience. It offers a framework for understanding creation and divine purpose that transcends material explanation, allowing believers to accept sacred narratives and divine agency without requiring empirical validation. Within Christianity, for instance, faith in the Genesis account is less about scientific proof and more about embracing a spiritual truth that connects humanity to its creator and imbues existence with meaning and moral direction. It invites believers into a relationship with the divine that transcends facts and figures, engaging the heart and soul in a timeless story of origin, purpose, and destiny. Thus, the dialogue between free will, evil, and creation myths is not merely an abstract philosophical exercise, but a living tapestry reflecting humanity's deepest hopes, struggles, and quest for meaning. It invites each of us to ponder the mysteries of existence and our place within the vast cosmos, encouraging us to seek understanding beyond what is immediately visible and to wrestle with the profound questions that have shaped human thought across millennia. But understanding the moral and spiritual lessons embedded in the narrative of creation reveals far more than just origins. It invites us into a profound relationship with a divine creator, one who is not distant or indifferent, but deeply loving, purposeful, and intimately involved with all aspects of existence. Faith in this light becomes a lens through which life gains meaning, order, and a sense of destiny. It anchors the human experience within a greater cosmic story, one where every event, every moment holds significance beyond mere chance. Similarly, in Hindu traditions, faith takes a nuanced form rooted in ancient scriptures like the Rig Veda and the Upanishads. These texts reveal metaphysical truths about the nature of reality, the divine, and the self, inviting followers to trust in cosmic principles such as Brahman, the ultimate formless reality, and Dharma, the ethical order that sustains life in the universe. This faith transcends simple belief. It offers a framework that reconciles the complex interplay between the physical and spiritual realms, even when these truths extend beyond human comprehension. The faith expressed here is not blind acceptance, but a deep trust in the harmonious order that governs all things, visible and invisible. Moreover, faith often intersects with scientific inquiry in compelling ways. While cosmologists unravel the mysteries of the Big Bang and the universe's evolution, many individuals of faith interpret these discoveries as reflections of divine creation. This convergence does not dilute either perspective. Instead, it enriches both. Science uncovers the mechanisms, while faith provides purpose and meaning behind these mechanisms, inspiring awe and reverence for the cosmic wonders science reveals. In this integrative worldview, the marvels of quantum mechanics and astrophysics deepen spiritual significance, transforming our understanding of the universe from cold facts into a vibrant, interconnected whole. Faith also shapes the ethical and moral dimensions of how humanity relates to the universe. Belief in a creator or ultimate principle brings with it a sacred responsibility, a call to stewardship. This mandate urges respect for the earth and care for all living beings, recognizing them as part of a divinely ordered system. Faith-based ethics inspire conservation, social justice, and a commitment to nurture the natural world, fostering a profound sense of interconnectedness and duty that transcends self-interest. It is this moral compass that guides actions toward preserving the delicate balance of life on our planet, underscoring the intrinsic value of creation. Yet, the relationship between faith and science is not without tension. At times, scientific explanations appear to challenge traditional beliefs, prompting believers to grapple with apparent contradictions. These moments spark dynamic dialogue, encouraging reinterpretation and a reimagining of faith that embraces new evidence without abandoning core spiritual truths. Such interplay between reason and belief can deepen faith, making it more resilient and nuanced. This evolution acknowledges that spirituality and scientific understanding need not be adversaries, but complementary ways of exploring reality. Ultimately, faith's role in comprehending the universe's origin and nature is richly multifaceted. It fosters trust in a grand design, provides existential meaning, inspires ethical living, and harmonizes with scientific insights. Faith does not oppose reason. It broadens our inquiry to include those dimensions of human existence that empirical science alone cannot fully capture: the mysteries of purpose, morality, and the soul's connection to the cosmos. Turning now to the scientific theory of a self-creating universe, this idea posits a cosmos that may have arisen and evolved independently without the need for an external creator. Emerging from advances in cosmology, quantum mechanics, and theoretical physics, this perspective explores mechanisms by which the universe could spontaneously originate from nothingness or from intrinsic properties embedded in space-time and physical laws. A central concept in this theory is quantum cosmology, which suggests that quantum fluctuations in a vacuum state, far from being empty, could give birth to the universe itself. In this quantum vacuum, energy blips and fluctuations create the seeds of cosmic expansion, providing a naturalistic explanation for the universe's birth grounded in the enigmatic yet mathematically precise realm of quantum physics. This scientific viewpoint, while radical, does not necessarily negate spiritual interpretations. Instead, it challenges us to expand our understanding of creation, recognizing that the universe's origins may be woven from both the mysterious dance of subatomic particles and the profound metaphysical realities that faith traditions have long contemplated. Together, these perspectives invite us into an ongoing dialogue, one that enriches our quest to understand existence from both the seen and unseen realms. But rather teeming with potential energy and flickering particles, the cosmos at its inception was far from empty, an unfathomable sea of quantum possibility where the known laws of physics bend and blur. Visionary physicists such as Stephen Hawking and James Hartle pioneered groundbreaking models that envision our universe as a spontaneous quantum fluctuation, a transient ripple within the quantum vacuum that burgeoned into the vast cosmos we inhabit. This revolutionary concept aligns with the Big Bang paradigm, yet boldly dispenses with the need for a pre-existing space-time fabric or any external causal force, redefining the notion of cosmic origins. In this radical framework, the universe's birth emerges not from divine intervention or an absolute beginning, but from the intrinsic rules of quantum mechanics themselves. This view finds further support in the intriguing concept of the multiverse, a sprawling ensemble of universes, each forged spontaneously with its own unique physical laws and constants. Imagine a cosmic landscape where bubble universes emerge like effervescent spheres within a grander, ever-inflating cosmic expanse. Each bubble springs forth due to the unpredictable dynamics of quantum fields, continuously generating new realms in an eternal, self-perpetuating genesis. Here, the question of a singular starting point loses meaning, replaced instead by an infinite cascade of cosmic creation. Adding yet another dimension to this tapestry, the zero-energy universe hypothesis proposes that the total energy of the cosmos is perfectly balanced. Positive energy from matter counteracted precisely by the negative gravitational energy. This remarkable balance hints that the universe could have emerged from nothing, without violating any conservation laws, suggesting a self-sustaining genesis that requires no external input. The concept of quantum tunneling, championed by physicists like Alexander Vilenkin, offers a captivating mechanism. The universe could have tunneled into existence through quantum processes, circumventing the need for a prior state or a divine creator altogether. Central to these ideas is the no-boundary proposal, formulated by Hawking and Hartle, which reimagines the universe's timeline itself. Instead of beginning abruptly at a singular moment in time, the cosmos may instead resemble the smooth, edgeless surface of a sphere where time melds seamlessly into space, erasing any definitive temporal origin. In this vision, the universe is finite yet boundaryless, self-contained in its fabric, and self-generated by the natural laws woven into its very essence. While such theories do not exclude the possibility of a divine creator, they open profound new vistas, offering a universe that potentially explains its own existence purely through the principles of quantum mechanics, relativity, and cosmology. The quantum vacuum, far from being an empty void, is a bubbling, restless arena where particles flicker in and out of existence, governed by the uncertainty principle. These spontaneous quantum fluctuations could have catalyzed the birth of spacetime itself, spawning entire universes without any external cause. The theory of cosmic inflation, developed by Alan Guth and others, builds upon this quantum foundation, proposing that a fleeting high-energy state after the Big Bang drove an exponential expansion of space. During this inflationary epoch, quantum fluctuations might have created varied bubble universes, each inflating at different rates and evolving according to distinct physical laws. Our universe may simply be one such bubble among an endless multiverse. Moreover, spontaneous symmetry breaking in particle physics illustrates how the early universe transitioned from a highly symmetric, uniform state to the diverse and complex cosmos we observe today, all through natural processes governed by fundamental forces and particles. This elegant progression from simplicity to complexity underscores the power of natural laws to generate order and structure from primordial chaos. Together, these theories weave a compelling narrative. The universe's origin may be an inherent feature of the quantum and cosmological laws that govern reality itself. Without invoking external agents or creators, the cosmos might have bootstrapped itself into existence, a self-creating, self-sustaining phenomenon embedded in the very fabric of space, time, and energy. This profound possibility invites us to rethink our place in the cosmos, challenging centuries-old assumptions and opening the door to new, awe-inspiring understandings of existence itself. But rely on principles inherent to the very nature of reality itself, weaving together profound insights from quantum mechanics, general relativity, and cosmology. Scientists have constructed intricate models that reveal the universe's emergence as not just a possibility, but a natural, though deeply complex, consequence of the fabric of existence. This approach illuminates the astounding power of natural laws, laws that underpin the cosmos, to give rise to the vast, diverse, and exquisitely structured universe we find ourselves within. Symmetry breaking stands at the heart of these transformative processes, serving as a cornerstone in our understanding of how the universe could have effectively created itself. Rooted deeply in the realms of particle physics and cosmology, symmetry breaking describes a fundamental shift where a system initially exhibiting perfect symmetry, uniform and indistinguishable in all directions, transitions into a state where that symmetry is lost, giving birth to complexity and diversity. In the infant moments of the cosmos, just after the Big Bang, the universe was an unimaginably hot, dense, and energetic environment, defined by a pristine symmetry. All fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were thought to be unified, manifesting as one harmonious entity, indistinguishable across space and time. Yet as the universe expanded and gradually cooled, this perfect symmetry shattered. The forces we know today diverge through processes comparable to phase transitions, like water freezing into ice, marking the beginning of a richly differentiated cosmos. Take, for example, the phenomenon of spontaneous symmetry breaking, exemplified brilliantly by the Higgs mechanism in particle physics. The Higgs field, omnipresent and initially uniform, undergoes a transformation as the universe cools. Its symmetry breaks, and it acquires a non-zero value. This subtle yet monumental shift imparts mass to elementary particles, differentiating them and sculpting the fundamental building blocks of matter and forces. Without this event, the universe would be a far cry from the intricate and structured reality we observe. Symmetry breaking is equally vital during cosmic inflation, the rapid expansion phase of the early universe. Here, a scalar field, known as the inflaton field, initially displayed perfect symmetry, but quantum fluctuations, the tiny ripples born from the Heisenberg uncertainty principle, disturbed this uniformity, planting the seeds of random variations in energy density. These minuscule irregularities would grow under gravity's influence, eventually blossoming into the enormous cosmic structures, galaxies, stars, planets that punctuate the universe's vast expanse today. Furthermore, grand unified theories and the quest for a theory of everything push the boundaries even further, positing that symmetry breaking happened at energy scales beyond our current reach. These speculative frameworks suggest a primordial cosmos governed by a singular, unified set of laws, from which the complex web of forces and particles arose through successive symmetry-breaking transitions. This cascading sequence of symmetry breaking is more than a scientific concept. It narrates the universe's extraordinary journey from simplicity to complexity. It marks the unfolding of cosmic history, from a homogeneous, featureless state to a vibrant realm rich with diverse particles, forces, and structures. And while some aspects remain speculative, this paradigm continues to shape our deepest understanding of reality's origins, revealing how the grand tapestry of existence is woven from the elegant interplay of symmetry and its inevitable breaking. Some cosmological models suggest that the entire universe might have sprung forth from an exquisitely balanced, symmetric vacuum state, a realm that at first glance seems like pure nothingness. And yet, within this emptiness, quantum tunneling and fluctuations quietly stir, initiating a profound transformation. This delicate breaking of vacuum symmetry is not just a trivial shift. It represents the crucial moment when the universe transitions from a false vacuum, a metastable state resembling a cosmic pause, to an inflationary state, an explosive expansion that breathes space, time, and matter into existence. Symmetry breaking stands at the very heart of the universe's self-creation story. Imagine the cosmos as beginning in a state of perfect symmetry, where all forces and particles are indistinguishable and unified in a high-energy dance. Then, through a series of symmetry breakings, this pristine balance shatters, allowing fundamental forces, gravity, electromagnetism, and the nuclear forces, to emerge with their distinct characters. Particles acquire unique properties, masses, and charges, weaving complexity into the fabric of reality. This remarkable process explains how the universe evolved from a simple, uniform condition into the intricate, structured cosmos we observe today, a sprawling, dynamic tapestry of galaxies, stars, and life itself. Embedded deeply within the laws of nature, symmetry breaking reveals the elegant mechanism by which order arises from the raw potential of chaos. And yet, this cosmic tale is incomplete without recognizing the vital role of feedback loops, the engines of self-organization and self-creation. By definition, a feedback loop is a system where outputs circle back as inputs, dynamically shaping future outcomes. These loops can amplify change, positive feedback, or promote stability, negative feedback. In the grand cosmic theater, feedback loops are fundamental drivers of the universe's evolution, guiding processes from the birth of stars to the behavior of particles. Consider star formation in the early universe, a prime example of cosmic feedback in action. After the inflationary epoch, tiny quantum fluctuations seeded uneven density patches within the primordial gas. Gravity then acted as a cosmic sculptor, pulling matter into denser regions, which in turn attracted even more material. This positive feedback loop intensified the density until collapsing gas clouds ignited nuclear fusion, giving birth to the first stars. These stars, through nucleosynthesis, forged heavier elements, enriching the cosmic environment as they lived and died. This recycling of material set the stage for future generations of stars and planetary systems, ultimately providing the essential ingredients for complex chemistry and, eventually, life. On the microscopic scale, feedback loops shape the very nature of fundamental particles. The interaction between the Higgs field and elementary particles creates a delicate feedback system whereby particles acquire mass. This isn't a simple on-off switch, but a dynamic equilibrium where particles and fields continuously influence each other, maintaining the stability and behavior of matter as described by the standard model of particle physics. Zooming out to the colossal scale of cosmic structure, feedback loops continue to weave complexity. Gravitational interactions between galaxies, galaxy clusters, and the elusive dark matter form intricate feedback networks. These interactions, repeated over billions of years, give rise to the cosmic web, the vast, interconnected structure of the universe. Here, initial conditions ripple outward through iterative processes, generating the stunning diversity of cosmic forms we witness. Finally, feedback loops extend their influence into the realms of thermodynamics and statistical mechanics, where they help systems spontaneously self-organize from disorder into structured order. The concept of dissipative structures, introduced by Ilya Prigogine, illustrates how systems far from equilibrium can, through feedback mechanisms, develop organized patterns and behaviors. This principle not only informs our understanding of physical systems, but resonates across biological and ecological systems, highlighting a universal truth. Feedback loops are foundational to the emergence of complexity throughout nature. In weaving together these threads, from the quantum birth of the universe to the grand architecture of galaxies and the dynamic dance of particles, we uncover a cosmic narrative defined by symmetry, its breaking, and the ceaseless interplay of feedback. This story reveals the universe not as a static monument, but as a living, breathing system, continuously shaped by elegant, self-sustaining processes, a testament to the profound beauty embedded in the laws of nature. For example, chemical reactions occurring far from equilibrium often give rise to mesmerizing oscillatory patterns and intricate spatial structures. These dynamic behaviors are not random, but are carefully maintained by complex feedback loops, self-regulating mechanisms that stabilize and perpetuate these phenomena. Intriguingly, such principles of self-organization do not merely belong to the realm of chemistry or biology. They extend their reach deep into the cosmos, suggesting that the very structure and complexity of the universe itself might emerge from similar self-organizing feedback processes. Consider the epoch of cosmic inflation, a brief yet transformative period during which the universe expanded at an astonishing rate. During this inflationary phase, tiny quantum fluctuations normally confined to the subatomic realm were magnified to astronomical scales. These fluctuations acted as the primordial seeds from which all the vast cosmic structures we observe today, from galaxies to clusters, eventually grew. The dynamics of the inflationary field were governed by feedback loops where the local energy density influenced the rate of expansion, which in turn altered the energy density, creating a powerful and self-sustaining cycle that drove the rapid growth of spacetime itself. This intricate dance of feedback is not confined to cosmology. It lies at the heart of life's origin and evolution. Life's emergence is underpinned by a delicate interplay between environmental conditions and biological processes, forming a dense web of feedback loops that fuel adaptation and evolution. Organisms continuously interact with their surroundings, modifying ecosystems and in turn being shaped by them. This bidirectional flow of influence exemplifies how self-amplifying and self-regulating mechanisms foster the flourishing of life, driving complexity from simplicity. Feedback loops serve as fundamental engines of self-creation and evolution throughout reality. They operate through positive and negative mechanisms that enable initial conditions to unfold into increasingly complex structures and behaviors. Whether shaping the formation of stars and galaxies, governing the behavior of fundamental particles, or orchestrating the rise of consciousness, feedback loops underscore the iterative, interconnected nature of the cosmos. By decoding these processes, we begin to grasp how the universe self-organizes, weaving the intricate tapestry of existence we witness. Imagine a universe that essentially creates itself, a concept that pushes the frontiers of our understanding of existence. This profound idea is embodied in the theory known as the bootstrap universe. Scientifically, a bootstrap universe is a self-sustaining system, where the cosmos brings itself into being without any external cause. It is a mind-bending notion where the universe acts as its own origin, maintained by an intricate network of quantum-level feedback loops. Visualize this concept as a cosmic Ouroboros, the ancient serpent devouring its own tail. In this model, every aspect of the universe is deeply interconnected and self-consistent, with physical laws and constants stabilizing each other in a delicate cosmic balance. Quantum fluctuations, tiny random variations in energy, could have spontaneously generated particles and antiparticles that shape the universe's vast structure. This framework challenges conventional ideas of cause and of an effect, weaving a mystical yet scientifically robust narrative about the cosmos's origin. The allure of contemplating a universe not only governed by physical laws, but inherently generating and preserving those laws in an infinite, self-referential loop is profound. The bootstrap universe invites us to rethink the origins and fabric of reality itself, opening doors to new philosophical and scientific horizons. At the core of scientific thought lies causality, the principle that every effect has a cause. This concept underpins how we interpret the world around us. Yet applying this principle to a self-creating universe introduces profound complexity. In the bootstrap universe, causality takes on a cyclical, looped nature. Here, the universe is simultaneously cause and effect of itself, defying the linear cause-to-effect progression we're accustomed to. Imagine a river whose end is also its source, a continuous flow looping back into itself. On a cosmic scale, this suggests that time, space, and matter are interwoven in ways that transcend traditional chronological order. Quantum mechanics further enriches this picture, with particles existing in superpositions and entanglements, phenomena that do not violate but rather complement the bootstrap concept. In this remarkable vision, the universe's self-sustaining cycle preserves causality in a form far more intricate than previously imagined, revealing the deep mystery and wonder of existence itself, but rather operates within a far more intricate and profound framework, one where beginning and end merge into a singular, self-sustaining system. This paradigm challenges our deepest intuitions, proposing a cosmos that is not a mere backdrop for unfolding events, but a dynamic, self-initiating entity, continuously creating and recreating itself. In this vision, the universe with all its physical laws and constants does not simply exist. It emerges from a self-referential process that defies traditional cause and effect, inviting us to rethink not only how the universe began, but the very fabric of causality itself. Within this grand cosmic tapestry, information takes on a foundational role, shaping reality at its most fundamental level. At the quantum scale, what we perceive as matter is not simply particles and waves. It is deeply intertwined with information itself. This information transcends the everyday notion of data or knowledge. It forms the essence of how particles behave, interact, and ultimately manifest. Quantum particles exist in a hazy realm of probabilities until the moment they are observed, a process that collapses possibilities into definite outcomes. This act of observation is essentially an exchange, a dialogue of information between observer and observed. Taking this revolutionary idea further, the physicist John Archibald Wheeler proposed the concept of it from bit. According to Wheeler, every particle, every force field, even the very structure of space-time is grounded in binary choices, in bits of information. The universe in this light becomes a vast, ongoing computation, tirelessly processing and crunching data to sustain its own existence and dynamic evolution. Black holes provide a powerful illustration of these ideas. Known as cosmic vacuum cleaners that consume matter and energy, black holes also present a profound mystery. What happens to the information they swallow? Stephen Hawking's groundbreaking work on Hawking radiation suggested that black holes aren't eternal prisons. Instead, they slowly evaporate, emitting radiation that, in theory, carries away the information they absorbed, albeit in a highly transformed state. This insight bridges quantum theory, thermodynamics, and information theory, highlighting information's pivotal role in the universe's evolution. Extending beyond black holes, the framework of information theory reshapes our understanding of entropy and time's arrow. Entropy measures the disorder or the amount of unavailable information within a system. As entropy increases, usable information decreases, pushing the universe inexorably towards thermodynamic equilibrium. This reveals time as a directional flow of increasing informational complexity and decay, a narrative of transformation where the universe continually reorganizes and evolves. This perspective unlocks a mesmerizing view of reality, not as a static backdrop, but as a self-unfolding story, written in the universal language of information. Reality continuously shapes itself through an intricate dance of data, where cause and effect loop back in self-referential cycles, birthing new structures and dynamics from primordial interactions. Within this self-creating universe, emergent properties become key markers of complexity. Emergence describes how simple interactions at microscopic scales can spontaneously give rise to astonishingly complex behaviors and forms at larger scales. Here, the whole transcends the sum of its parts. Simple quantum rules spark fluctuations that grow into particles, atoms, molecules, and ultimately vast cosmic systems, galaxies, stars, and planets. These emergent structures provide the fertile ground for even richer phenomena to arise. Consider, for example, theoretical models like the bootstrap universe or the holographic principle, which suggest a cosmos where self-creation is encoded in its very fabric. At the smallest scales, quantum fluctuations act as seeds from which the entire universe blossoms. These minuscule, spontaneous changes ripple outward, guiding the evolution of fundamental forces, gravity, electromagnetism, and the nuclear forces that govern the stability and diversity of matter and energy. But this story of emergence goes beyond inert matter. Life itself emerges as an extraordinary consequence of these fundamental interactions. The same cosmic processes that forge stars and galaxies also enable the complex biochemical networks necessary for living organisms. Consciousness, in this view, arises as an emergent property of these interactions, representing a pinnacle of informational complexity and self-awareness. Through this lens, the universe's self-creating nature is a perpetual cycle of genesis and evolution, where emergent properties serve as milestones along an ever-unfolding narrative. It invites us to see existence not as a one-time event, but as an ongoing process of creation, a cosmic story without a definitive beginning or end. The philosophical implications of such a universe are profound. It challenges classical notions of causality and existence itself. If the universe creates itself, then the need for an initial external cause or creator comes into question. This shifts our understanding of origins away from linear, singular events like the Big Bang toward a cyclical or self-referential paradigm where the universe is an eternal dance of creation, destruction, and rebirth. Ultimately, this vision compels us to reconsider our place in a cosmos that is not static, but alive with information, continuously shaping itself through an infinite web of interconnections. A universe that is, at its core, a magnificent, self-generating mystery. But what if the universe is not a simple sequence of events unfolding from a single origin, but an ongoing process where cause and effect weave together in an eternal loop? This profound concept challenges the very foundation of how we understand existence, blurring the lines between beginning and end, cause and consequence. It invites us to reconsider the nature of consciousness and observation, proposing that these are not mere spectators in the cosmic drama, but active participants shaping reality itself. If the universe is indeed self-creating, then the act of measurement, the observer effect in quantum mechanics, transcends passive observation and becomes a dynamic force. Through observation, quantum states collapse from possibility into actuality, meaning consciousness may be deeply intertwined with the fabric of matter. This suggests a cosmos incomplete without observers to interact with it, where the universe and conscious beings form an inseparable dance of creation and manifestation. This aligns with interpretations like the Copenhagen interpretation of quantum mechanics, which holds that particles exist only in probabilities until observed. Moreover, this self-generating cosmos supports a holistic view of existence, one where everything is connected in an immense network of informational exchanges and feedback loops. Every action, however small, sends ripples through the entire matrix of reality, reminiscent of the butterfly effect in chaos theory, where a butterfly flapping its wings can ultimately influence weather patterns continents away. Philosophically, this paints the universe as a living, self-resolving entity, where meaning and purpose emerge naturally from the interactions of its parts, rather than being imposed from an external source. This view also invites us to rethink human existence itself. Instead of seeing ourselves as mere products of a predetermined cosmic plan, we might embrace the role of active co-creators within an evolving universe. This sense of participation carries profound responsibility, highlighting the impact of our choices not only on ourselves but on the cosmic scale. It inspires a moral framework grounded in interconnectedness and stewardship, reminding us that our actions echo through the vast web of reality. The notion of a self-creating universe stands in stark contrast to traditional views rooted in linear causality and external creators. Classical religious and philosophical doctrines often posit a prime mover, a deity or metaphysical principle, as the original cause that set the cosmos into motion. This creates a narrative with a clear beginning, typically framed as the moment of creation, followed by a linear unfolding of history. In opposition, a self-creating universe is its own cause, cycling endlessly without a definable starting point. It sustains itself through feedback loops and self-organizing principles, negating the need for an external agent. Modern scientific theories resonate with this idea. Concepts such as the multiverse hypothesis propose that our universe is but one of many, each self-perpetuating and evolving by its own intrinsic laws. The holographic principle even suggests that the universe's information is encoded on a boundary, pointing toward a reality where space, time, and matter emerge from deeper, underlying processes. From a metaphysical standpoint, this shifts our understanding of purpose and design. Traditional cosmologies often ascribe intrinsic meaning and direction to the cosmos, anchored by an external creator or teleological principles. However, A self-creating universe posits that meaning and purpose are emergent, arising from the complex web of interactions within the universe itself. Complexity, consciousness, and even ethics evolve naturally as byproducts of this ongoing creative process. Ultimately, the self-creating universe transforms the narrative of our place in existence. We move from being passive observers within a predetermined framework to becoming vital participants in an infinite, dynamic dance of creation. This perspective challenges us to embrace mystery and possibility, urging us to reflect on questions that have fascinated humanity for millennia. Did the universe truly begin from nothing? Are we alone in this vast expanse? And if the universe is indeed a self-sustaining, self-creating phenomenon, what does that mean for our role as conscious beings? Share your thoughts and reflections with us in the comments below. If you find this exploration captivating, subscribe to our channel, Starflux, for more journeys into the mysteries of existence. Thanks for watching.